Something stirs in the endless blackness of space, small, cold, observing. Not a monster, not a looming threat in the sense we imagine, but something far stranger, far more enigmatic. A star. Just 7.9 light years away, practically a neighbor on the cosmic block, silently spinning in the void. Our distant companion drifts through the galaxy unnoticed, a tiny, dim ember against the brilliance of the Milky Way, and yet it is capable of forces that would make our sun look like a gentle candle. Place it where the sun now warms our world, and Earth would ignite, charred and consumed within moments. This is a red dwarf, a class of star that seems unremarkable at first glance. Smaller, cooler, and less luminous than our sun, often less than half its mass. Yet beneath that modest exterior lies extraordinary power. Red dwarfs are unpredictable. They flare violently without warning, magnetic storms tearing across their planetary systems, radiation that could strip atmospheres and annihilate life in seconds. For decades, astronomers thought they were innocuous, even quaint. But then the data arrived, bursts of energy, intense magnetic fields, and the unsettling revelation that even a star of such modest size can wield catastrophic potential. The star I am describing sits just 7.9 light years from Earth, less than 8 if you are counting, practically next door in cosmic terms. It exists quietly in the vastness of space, a dim glow hidden among billions of other stars. You won't spot it twinkling in the night sky. It doesn't announce itself with the glory of the sun or the majesty of Sirius. In fact, most casual stargazers have never even heard its name. But you should know it. Wolf 359. The name carries a certain science fiction gravitas, evoking fleets of starships and epic galactic battles, and indeed Wolf 359 has appeared in fiction, most famously in Star Trek, immortalized in one of the franchise's most notorious conflicts. But the real Wolf 359 is no fiction. It is real, a tangible celestial neighbor drifting in the cosmic sea, unassuming yet capable of the extraordinary. It is remarkably small, so small and dim that searching for it with the naked eye is impossible, and even through a decent amateur telescope it is a challenge to locate. It hides in plain sight, closer to us than almost every other star, yet shrouded in obscurity, a ghostly presence at the doorstep of our solar system. Wolf 359 is classified as a red dwarf, the most common type of star in the galaxy. But common here is deceptive. Red dwarfs are understated, modest stars with soft, ruddy glows, their brilliance barely a whisper compared to the roaring intensity of the sun. They burn slowly and live extraordinarily long lives, often trillions of years, far outliving most stars in the universe. In the cosmic scheme, red dwarfs are the retirees of the stellar world, enduring and persistent, quietly shaping the galaxy for eons. Among the closest stars to Earth, Wolf 359 sits just behind the Alpha Centauri system and Barnard star. It is remarkably near, astronomically speaking, yet its modest luminosity keeps it hidden. Its feeble radiance, less than 1% of the sun's, makes it nearly invisible in the night sky. Imagine the sun as a roaring campfire, blazing and bold. Wolf 359 is a glowing ember tucked beneath a log, radiating its faint light silently into space. One of our nearest neighbors is almost undetectable, an invisible sentinel in the darkness, a humbling reminder that the universe holds countless secrets just beyond our perception. Astronomers prize Wolf 359 for this very reason. Its modesty provides a glimpse into the true majority of stars in the Milky Way, the countless red dwarfs that outnumber all others yet rarely capture attention. For scientists, it is a natural laboratory. For storytellers, it is a dream, a hidden star so close to home, potentially dangerous, possibly harboring alien worlds and cloaked in mystery. Yet Wolf 359 is not merely a background actor. Red dwarfs, especially young ones, are volatile. They erupt in sudden, violent flares, magnetic storms that tear through space, with radiation capable of stripping atmospheres in moments. A red dwarf may appear calm and diminutive, but it hides a volatile temperament, a celestial temper ready to ignite without warning. Could Wolf 359 threaten Earth? Not in the way science fiction might suggest. It will not explode into a supernova to engulf us, nor collapse into a black hole to consume the planet. Yet in extreme circumstances, its eruptions could send radiation surges capable of disrupting satellites, frying electronics, and endangering astronauts exposed beyond our protective magnetic shield. Consider an unsettling thought experiment. What if Earth orbited Wolf 359? Our world would freeze under its dim light, trapped in perpetual twilight beneath a crimson sky. Photosynthesis would falter, temperatures would plummet, and oceans could begin to freeze. Life as we know it might collapse. Yet, red dwarfs can host planets in close orbits where heat is sufficient to sustain life. In theory, life could cling to a world under Wolf 359's red glow, adapting to periodic flares and the muted light. Astronomers have searched for planets around Wolf 359. Its dimness actually makes planets easier to detect. A small world passing in front of the star blocks a proportionally large fraction of its light, revealing its presence. So far, none have been confirmed, but the search continues. If a planet existed in a safe orbit, warm enough to avoid destruction, yet close enough to capture sufficient energy, it could potentially harbor life. Strange, alien, resilient life unlike anything on Earth, evolved to endure red flares and thrive in crimson twilight. Wolf 359 is also young in cosmic terms, a mere toddler compared to our middle-aged sun. Just a few 100 million years old, it burns with youthful energy, a sparkling child of the galaxy with a volatile spirit, unpredictable and alive. In contrast, the sun's steady, age-old glow seems almost tame. In the end, Wolf 359 embodies the paradox of red dwarfs, small, quiet, almost invisible, yet capable of unimaginable power. It sits in the cosmic darkness, silently observing, a reminder that the universe is vast, mysterious, and full of secrets that wait, patiently, for discovery. But here's the real twist. Long after our sun has exhausted its nuclear fuel and turned into a cold, dark remnant, long after Earth has been stripped to a frozen husk or perhaps even vaporized entirely during the sun's red giant phase, Wolf 359 will remain. Quiet, persistent, unyielding. For trillions of years, this unassuming star will continue its slow, patient burn, an enduring ember in the cosmic night. And this isn't a poetic flourish, this is the reality of red dwarfs. Some astronomers theorize that the last visible lights in the universe might not be grand, dazzling supernovas or luminous giants, but modest red dwarfs like Wolf 359 flickering stubbornly as the universe grows cold and silent. When we say this star could outlast everything we know, we mean it in the most literal sense imaginable. And yet, this astonishing longevity comes from a star so tiny and inconspicuous, so unassuming, that it resides just 8 light years away from us. 8 light years. That's practically our celestial backyard. Wolf 359 is both ghostly and paradoxical, so near yet nearly invisible, so dim yet eternal, so small yet brimming with secrets we are only beginning to uncover. And it is here, in this quiet corner of space, that our journey begins. Over the course of this exploration, we will peel back the layers of Wolf 359, examining the intricate life cycles of red dwarfs, delving into the physics behind their sudden, violent stellar flares, and confronting the profound questions they pose. Could such a modest star conceal planets capable of supporting life? Could it teach us lessons about building civilizations that span the stars? Could it one day serve as a cosmic refuge when the more familiar parts of the galaxy have faded into darkness? Fasten your seatbelts. We are venturing into the subtle but unrelenting fire of the universe, starting with a star you've likely never noticed, but absolutely should. Here it is, Wolf 359. Its name lacks the lyrical resonance of Sirius or Betelgeuse, and it certainly won't dominate any stargazer's conversation. Staring directly at its location in the night sky, you would see nothing, because Wolf 359 is shy, one of the faintest stars in our local celestial neighborhood. And yet, paradoxically, it is one of the nearest stars to Earth, only 7.9 light-years away. To put that in perspective, in cosmic terms, that is practically next door. So, what exactly is Wolf 359, and why does this seemingly insignificant red dot captivate astronomers, inspire science fiction, and command our attention today? Wolf 359 is a red dwarf, a member of the M-class stars, more precisely classified as M6. 5. Think of this as its stellar personality profile. The M identifies it as a red dwarf, while the 5 indicates that it is at the extreme cooler end of that already cool spectrum. And when we say cool, we mean temperature. Wolf 359's surface hovers around 2800 Kelvin, roughly half the temperature of our sun. If the sun is a blazing white-hot furnace, Wolf 359 is a glowing ember, radiating a soft, reddish warmth. Its size is equally striking. Wolf 359 carries just 9% of the sun's mass and spans less than 15% of its diameter. Side by side, the sun would appear as a massive beach ball, while Wolf 359 would barely register as a marble beside it. Yet, despite its modest size and luminosity, this little star packs a universe of intrigue. Though it is the fifth closest star system to Earth, it remains invisible to the naked eye, barely surpassing the threshold of visibility even under the darkest skies with the most sensitive telescopes. Red dwarfs, in essence, are the introverts of the cosmos. Small, quiet, and slow-burning, they live life at their own unhurried pace. Massive stars burn bright and die young, exploding as supernovas or collapsing into black holes. Red dwarfs like Wolf 359 are the patient survivors, burning steadily for trillions of years. To contextualize, our sun's estimated lifespan is about 10 billion years. Wolf 359 will endure 100 times longer, and yet it is only a few 100 million years old, a toddler by cosmic standards. This slow, measured existence makes red dwarfs fascinating in their own subtle way. They may not scream with explosive drama, but their stability and endurance speak volumes about the cosmos' quieter, uncelebrated marvels. Yet do not mistake this stability for monotony. Even the quietest of stars have their outbursts. Wolf 359 is a flare star, occasionally erupting in violent bursts of energy that can dramatically increase its brightness in mere minutes. Imagine drifting near it in a spacecraft, observing a tranquil crimson dot, and then, without warning, seeing it flare into a mini explosion of light and radiation. These outbursts, far more intense than any solar flare our sun produces relative to size, are driven by complex magnetic interactions beneath the star's surface. Like tangled rubber bands snapping, the magnetic fields unleash tremendous energy, transforming a modest ember into a momentary cosmic firework. For any planet orbiting Wolf 359, these flares are no trivial matter. One moment, the sky glows a faint red. The next, it is flooded with potentially lethal radiation. Not exactly prime real estate for life as we know it, but precisely these extremes make Wolf 359 a subject of immense scientific fascination. Its faint luminosity, barely 0.1% that of the sun, explains why most people have never heard of it. If the sun were a 100-watt bulb, Wolf 359 would be a mere tenth of a watt nightlight. Despite its proximity, it remains largely invisible, a quiet enigma next door. Its discovery came thanks to German astronomer Max Wolf in the early 20th century, using photographic plates to track stars with high proper motion, stars that visibly drift across the sky. He cataloged Wolf 359 as entry number 359. The name may sound like a Star Trek coordinate, but it is simply a methodical recording of a curious, fast-moving neighbor. Wolf 359 shares its cosmic neighborhood with stars like Proxima Centauri, Alpha Centauri A and B, Barnard's star, and the binary brown dwarf system Lumen 16. Yet unlike some of its companions, Wolf 359 does not form a binary or trinary system. It drifts alone, a solitary red ember navigating the darkness, a lone figure with occasional flare-driven tantrums surrounded by the cold void. There is a quiet poetry in its existence, a star that simultaneously reflects the universe's history and its distant future. It represents the ancient simplicity of early star formation while remaining young and vibrant by cosmic standards. Billions of years hence, long after the sun has faded to black, Wolf 359 will still be there, dimly glowing, a lone candle flickering in a silent universe. It teaches patience, endurance, and quiet power, the cosmic lesson that survival is sometimes the greatest form of triumph. It reminds us that the universe's most enduring forces are not always the brightest or the largest. Red dwarfs dominate our galaxy, making up an estimated 75% of all stars. 3 out of every 4 stars you cannot see are likely tiny red dwarfs like Wolf 359. And within this vast population, one cannot help but wonder, could some harbor planets, perhaps even life quietly orbiting far from our view? Could Wolf 359 or its siblings conceal worlds yet to be discovered? When we think of stars, our minds leap to the sun, bright, life-giving, familiar. But the universe has far stranger, more subtle examples, and red dwarfs are at the forefront. Small, cool, and mysterious, with surface temperatures ranging from about 2,500 to 4,000 degrees Celsius, equivalent to roughly 4,500 to 7,000 degrees Fahrenheit, they burn not with blazing heat, but with the persistent, smoldering glow of embers, quietly shaping the cosmos in ways we are only beginning to understand. And yet, it is precisely this unusually low temperature that sets red dwarfs apart from the stars we are most familiar with, those like our own radiant sun. Unlike the blazing heat of stars in the main sequence's upper echelons, red dwarfs simmer gently, glowing faintly in the cosmic night. But the peculiarities of these stars extend far beyond mere temperature. Their energy production, the nuclear fusion at their cores, is remarkably slow. Where our sun converts hydrogen into helium at a frenetic pace, red dwarfs perform this same alchemy at a lethargic, almost leisurely rate. This unhurried fusion grants them lifespans that stretch across scales of time, almost unimaginable to the human mind. While our sun is projected to persist for roughly 10 billion years, a typical red dwarf can endure for trillions of years, trillions, with the result that these small, unassuming stars could continue shining long after galaxies themselves have grown dim. Their extraordinary efficiency and fuel consumption makes them the stellar embodiment of longevity. Red dwarfs burn so slowly that their hydrogen reservoirs last eons, enabling them to maintain stability over timescales that dwarf those of larger, more energetic stars. In fact, many astronomers regard red dwarfs as the most stable stars in the universe, steady and enduring in a way that almost seems deliberate. They are the tortoises of the cosmic realm, a stark contrast to our sun. While our sun will eventually swell in a dramatic finale as a red giant, exploding outward in a fiery crescendo before settling into the quiet embers of a white dwarf, red dwarfs conclude their existence with an understated grace, fading gently into dim, cold remnants long after the universe has aged considerably. And yet, these otherwise tranquil stars harbor moments of unpredictable fury. Red dwarfs are prone to flare activity, sudden violent bursts of energy that erupt from their surfaces. These flares mirror in concept the solar flares we occasionally witness from the sun, but they are often far more intense, both in magnitude and frequency. A single red dwarf flare can unleash energy thousands of times greater than the mightiest flare from our sun, sending torrents of radiation and high-energy particles streaking into the surrounding space. Such outbursts are breathtaking in scale, but can pose a threat to any planetary bodies orbiting nearby, bombarding them with conditions inhospitable to life as we know it. Despite their size, luminosity, and occasional volatility, red dwarfs occupy a crucial position in our quest to understand exoplanets, worlds orbiting stars beyond our own solar system. A significant fraction of the exoplanets discovered so far circle these modest stars, largely because red dwarfs are both abundant and remarkably enduring. Their stability creates a cosmic environment where planets can form, evolve, and potentially sustain life for epochs far longer than planets around hotter, shorter-lived stars. For those searching for extraterrestrial life, red dwarfs present compelling targets. Though they are smaller and cooler than our sun, they have a profound influence on their orbital companions. Planets too close may be scorched by stellar flares, yet those at a sweet spot, neither too near nor too distant, might harbor conditions favorable to liquid water, the essential ingredient for life as we understand it. This delicate equilibrium elevates red dwarfs from mere cosmic oddities to pivotal players in the pursuit of habitable worlds. In essence, red dwarfs are understated yet vital components of our galaxy. They are quiet workhorses of the Milky Way, long-lived, resilient, and brimming with mysteries yet to be unraveled. They are diminutive and cool when compared to our sun, yet they vastly outnumber their more ostentatious stellar cousins, dominating the galactic population. And though their presence may lack the fiery spectacle of supergiants and massive main-sequence stars, they tell a story of endurance and hidden significance, one that continues to unfold with each new observation. As technology advances, astronomers anticipate uncovering even more secrets of these stars, revealing complexities and behaviors that have remained invisible for centuries. Consider Wolf 359, one of the nearest red dwarfs to Earth, located a mere 7.9 light-years away. Its proximity might suggest that it should shine visibly in our night sky, yet it remains entirely invisible to the unaided eye. Standing in a clear open field, one could gaze skyward without any hint of its presence. Wolf 359 emits such faint light that its apparent magnitude plunges to 13.5, a stark contrast to the stars that dazzle us nightly, like Sirius, whose brightness measures at 1.5. The lower the number, the brighter the star, and at 13.5, Wolf 359 exists in the realm of subtlety, barely discernible even to seasoned observers without specialized equipment. Discovered in 1917 by German astronomer Max Wolf through meticulous photographic observations, Wolf 359 exemplifies the hidden significance of red dwarfs. Though faint, this star has become an important cornerstone in our understanding of the galaxy's less conspicuous stellar population. Its discovery marked the beginning of a journey to appreciate the quiet, persistent presence of red dwarfs, their extraordinary lifespans, and their potential role in shaping the conditions for life across the cosmos. And so, while Wolf 359 may drift silently through the void, almost invisible to human eyes, it represents a cosmic story of endurance, stability, and the subtle power of stars that quietly outlast all others, guiding astronomers toward a deeper comprehension of the universe's long, intricate narrative. It's astonishing to consider that what once appeared as a nearly imperceptible pinprick of light in the sky has, over the decades, become one of the most captivating stars for astronomers and stargazers alike. When we look at the night sky today, Wolf 359 does not announce itself with brilliance. You won't spot it with a casual glance or even through an ordinary pair of binoculars. To truly observe it, you need instruments that can reach deep into the cosmos, telescopes capable of gathering faint light from stars that lie many light years away, bringing them into sharp focus. Facilities like high-resolution modern observatories, or space-based telescopes such as Hubble, provide the clarity required to witness this quiet celestial neighbor. Wolf 359 is not a star that reveals itself easily. It demands both the right equipment and the knowledge to interpret its faint signals. Yet the fascination with Wolf 359 extends far beyond its subtle glow. Its intrigue lies in its motion through space. Despite its dimness, Wolf 359 moves with astonishing speed across the heavens. Astronomers describe this as proper motion, the apparent movement of a star relative to the more distant background stars. If one could watch Wolf 359 over years or decades, it would appear to drift steadily across the cosmic stage, a true cosmic wanderer. Unlike most stars that seem fixed in place against the backdrop of the universe, Wolf 359 is constantly on the move, as if striving to escape the vast emptiness that surrounds it. This motion is not a fleeting phenomenon. It has been ongoing for millennia and will continue long into the future. Eventually, in a timescale far exceeding a human lifetime, Wolf 359 could drift closer to our solar system. Its journey reminds us that the stars we often consider permanent fixtures are, in reality, travelers navigating the immense cosmic ocean. The night sky is not a static canvas. It is alive with motion, with stars constantly shifting and reshaping the patterns we see from Earth. Consider for a moment the quiet existence of Wolf 359. Even though it is comparatively close in astronomical terms, it remains invisible to the naked eye. It is a whisper in a crowd of cosmic giants, a humble star that contrasts sharply with the dramatic supernovae, radiant nebulae, and massive luminous stars that dominate our imaginations. Wolf 359 embodies a cosmic humility. It exists not to dazzle, but to persist quietly, steadily, and without notice. While the universe may seem populated with stars seeking attention, Wolf 359 reminds us that significance does not require flamboyance. Its presence urges reflection on the nature of the universe, where the most unassuming elements can hold profound meaning. This quiet red dwarf is more than a faint light in the sky. It is a key figure in the broader story of red dwarfs, the small, long-lived stars that make up the majority of stars in our galaxy. While human attention often gravitates toward spectacular and dramatic stars, it is these steady, slow-burning dwarfs like Wolf 359 that dominate the cosmic landscape. Their importance becomes clear in the search for exoplanets, the quest to discover life beyond Earth, and the effort to understand the workings of our universe on a fundamental level. Though unseen by casual stargazers, Wolf 359's existence plays a pivotal role in the grand cosmic narrative. Wolf 359's story does not end with astronomy. It has also left its mark on human culture, particularly in science fiction. For fans of Star Trek, the name Wolf 359 evokes an epic battle, a key moment in the saga of the Federation's struggle against the Borg. In the two-part episode, The Best of Both Worlds, Wolf 359 is immortalized as the site of a climactic conflict, symbolizing both danger and strategic importance. While this portrayal is fictional, the choice of a real star lends the story authenticity, grounding fantastical narratives in the tangible reality of our universe. Real celestial bodies, with their histories and inherent mysteries, enrich fiction by providing a credible backdrop for human imagination. Wolf 359's presence in science fiction is not limited to Star Trek. It appears across novels, films, and games as a distant, enigmatic point of reference, embodying the same sense of isolation, mystery, and cosmic significance. Works like the Expanse series evoke similar themes, portraying a universe filled with distant stars, unexplored planets, and the persistent unknown. While Wolf 359 itself may not be named, the essence of red dwarf systems, small, faint, yet crucial, is echoed throughout these stories, connecting fiction with the real cosmos. Through both science and culture, Wolf 359 serves as a bridge between the observable universe and human imagination. Its faint light challenges us to look deeper. Its motion reminds us that nothing in space stands still, and its quiet existence encourages a reflection on humility amid grandeur. Far from being a mere point of light, Wolf 359 is a testament to the hidden wonders that await discovery, a silent voyager through space, and a symbol of the unassuming yet profound mysteries that the cosmos holds. But it's not only Star Trek or The Expanse that have seized upon the story of Wolf 359. Across the panorama of science fiction, red dwarf stars like Wolf 359 have captured the imagination of writers, artists, and dreamers alike. In these narratives, red dwarfs are more than just tiny points of light in the night sky. They often become symbols of endurance, mystery, and sometimes quiet menace. Some stories depict them as ancient, dying embers, remnants of once vibrant stellar neighborhoods, now inching slowly toward an inevitable, almost imperceptible extinction. In other tales, these stars are agents of danger, their erratic flares or bursts of radiation posing lethal threats to nearby worlds. The blend of real astrophysical principles and imaginative extrapolation allows authors to turn these modest stars into narrative tools capable of evoking awe, dread, or even philosophical reflection. Red dwarfs in fiction rarely remain mere backdrops. They can become icons of forgotten cosmic eras, like silent witnesses to the slow march of time across trillions of years. They can be portrayed as post-apocalyptic suns illuminating planets long abandoned, or as strange cosmic forces capable of both creating and destroying life. These depictions resonate because they straddle the boundary between what we understand and what we can only speculate, embodying both the familiar patterns of stellar physics and the alien possibilities of deep space. But the allure of red dwarfs extends beyond storytelling. Astronomers and astrophysicists are equally captivated, especially by their extraordinary longevity. Stars like Wolf 359 burn hydrogen at a glacial pace, allowing them lifespans that stretch into the trillions of years, far longer than stars like our Sun. This slow, steady burn imbues them with a sense of permanence and reliability, qualities that other, more flamboyant stars cannot match. In science fiction, this longevity becomes a canvas for exploration. Civilizations could thrive for eons around a red dwarf. Life could evolve in ways unimaginable on planets orbiting shorter-lived stars, and mysteries could unfold over stretches of time that dwarf human comprehension. Approaching a red dwarf, one might see only a dim, modest glow, a faint speck amid brighter celestial giants. Yet that unassuming dot carries the potential for extraordinary complexity. Its planets could harbor ecosystems, civilizations, or conditions that challenge our very understanding of life. In this juxtaposition of stability and danger, red dwarfs like Wolf 359 become perfect metaphors for the cosmic balance between the known and the unknown, between the comforting and the threatening. They exist in a kind of twilight zone, not the massive, short-lived blue supergiants that blaze brilliantly and die young, nor the violent, dying suns that erupt in spectacular supernovae. Red dwarfs endure quietly, persistently, through the vast expanse of time. Science fiction often amplifies this endurance, imagining ancient cultures thriving around these stars long after others have burned out. These civilizations could preserve knowledge, culture, and memory across billions of years, making red dwarfs anchors of cosmic history. The faint light from these stars becomes a vessel for ancient stories, whispering hints of what came before. And while much of this is imaginative speculation, the scientific reality is not far removed. Red dwarfs like Wolf 359 could indeed host planets capable of supporting life, making them prime targets for exoplanet research and the search for extraterrestrial civilizations. This intertwining of fact and fiction raises tantalizing questions. Could some of the civilizations imagined in science fiction actually exist? Could life thrive in the dim, distant glow of a red dwarf? The answer remains uncertain. Exploration and observation are the only ways to find out. In this interplay, fiction fuels scientific curiosity, and scientific discovery enriches the imaginative worlds of writers. Wolf 359, in both science and culture, is still revealing its story, and its role in human imagination is far from complete. Yet alongside these speculative tales, the more dramatic and apocalyptic images persist. Stars consuming planets whole, engulfing worlds like cosmic predators. Wolf 359, a red dwarf merely 7.8 light-years from Earth, can inspire such images. But if we step back and examine the physics, reality is less cinematic but no less fascinating. Wolf 359 is diminutive compared to our Sun, only about 1/7 its size, far too small and cool to pose a direct threat to Earth. To swallow a planet, a star must expand dramatically, a fate awaiting some stars in the red giant phase, but not red dwarfs like Wolf 359, which follow slow, steady life cycles lasting billions or even trillions of years. Even entertaining a hypothetical approach of Wolf 359 toward our solar system exposes the vast improbabilities involved. Stars drift along their own paths within the Milky Way. The distances between them are immense. Wolf 359, at nearly 8 light-years away, is not wandering dangerously close. A rogue star passing near a solar system, while rare, could disrupt distant icy bodies in the outer reaches, potentially sending comets careening inward. Such scenarios might reshape planetary environments, but they are not the same as a star actively consuming a planet. Realistic danger from a red dwarf comes not from size or proximity, but from stellar activity, flares and radiation that can erode atmospheres and challenge life on close orbiting worlds. This subtle but persistent threat is the kind that captivates both astronomers and storytellers. Life on planets orbiting a red dwarf would need to endure constant flare storms, survive fluctuating radiation levels, and adapt to dim light, producing ecosystems unlike anything on Earth. For us, at a comfortable distance from Wolf 359, these dangers are theoretical, yet they fuel speculation and imagination alike. When stars die or evolve, they can impact nearby planets, expanding outward and reshaping their systems. The Sun itself will one day become a red giant, gradually engulfing Mercury, Venus, and possibly Earth, but this is a slow, inevitable process, not an immediate threat. Wolf 359, by contrast, will remain stable for billions of years, quietly burning its fuel and maintaining its presence as a long-lived sentinel of the galaxy. Its story is one of endurance, subtle influence, and potential. And whether in the realms of science or fiction, Wolf 359 continues to inspire wonder, curiosity, and speculation about what might exist in the far reaches of the cosmos. However, in the distant reaches of cosmic time, as stars age, evolve, and ultimately transform, the universe we observe today will not remain static. Imagine a future where the calm, steady glow of stars gives way to dramatic events, supernovae explosions, violent ejections of stellar material, or sudden bursts of radiation. If Wolf 359, a seemingly unassuming red dwarf, were to experience such a cataclysmic event, the consequences would ripple across space. Waves of high-energy particles and intense radiation could sweep through its stellar neighborhood, interacting with planets, asteroids, and other celestial objects, reshaping their orbits and potentially triggering new cosmic phenomena. Yet it is crucial to remember that for the foreseeable eons, Wolf 359 poses no direct threat to Earth. The hypothetical scenarios we explore, though thrilling in their imaginative scope, are more thought experiments than imminent dangers. Still, the cosmos contains genuine hazards closer to home. Stars like Gliese 710 illustrate this point vividly. In approximately 1.3 million years, Gliese 710 is predicted to pass within a mere 1.3 light-years of our Sun. While a collision is not on the cards, its gravitational influence could disturb the distant Oort cloud, sending icy comets hurtling toward the inner solar system and subtly shifting planetary orbits. These possibilities serve as reminders that the universe, though largely tranquil, harbors the potential for surprises that could ripple across billions of kilometers. As we contemplate these cosmic dynamics, it is natural to shift our curiosity from existential threats to the tantalizing prospects of life beyond our solar system. The red dwarf Wolf 359 prompts one of the most profound questions in astronomy. Could life exist around stars so different from our Sun? Red dwarfs are the silent majority of the galaxy, comprising roughly 70% of all stars in the Milky Way. With such ubiquity, the likelihood that planets capable of supporting life orbit these stars becomes not merely possible, but statistically probable. However, the conditions surrounding red dwarfs are unlike those experienced by Earth. The so-called habitable zone, the narrow orbital belt where liquid water can exist, is squeezed perilously close to the star. This proximity brings both opportunity and danger. Planets within this zone often face tidal locking, where one hemisphere perpetually bakes under the star's glare while the opposite side is plunged into endless darkness. Surface temperatures could be extremes, molten, scorching landscapes on the day side and frozen wastelands on the night side. Life as we know it would struggle to survive under such harsh conditions, yet the resilience of life on Earth hints at possible adaptations elsewhere. Consider the twilight band between the scorching and frozen hemispheres, often called the Terminator line. This narrow region may host temperate conditions, a potential cradle for life resilient enough to endure the star's constant radiation and the limited spatial range of habitability. Organisms here would face evolutionary pressures unlike any on Earth, potentially developing reflective surfaces to shield against radiation, or biochemical mechanisms to repair DNA damaged by relentless stellar flares. Red dwarfs are notorious for these flares, sudden outbursts of energy that can strip atmospheres, sear surfaces, and challenge the survival of nascent life forms. Exploring the variety of planets around red dwarfs adds layers of complexity and fascination. Some may be rocky worlds reminiscent of Earth, others might be vast oceanic planets, water worlds where life has evolved entirely within the depths of oceans. The TRAPPIST-1 system offers a tantalizing case study. 7 Earth-sized planets orbiting a red dwarf approximately 40 light-years away, some within the habitable zone, presenting opportunities for liquid water to persist. Even closer, Proxima Centauri b orbits our nearest stellar neighbor and sits within its habitable zone, yet must contend with a star prone to violent activity, forcing life to adapt or perish. Life in these environments could depart radically from our terrestrial paradigms. Without a stable day-night cycle, biological rhythms would differ profoundly. Photosynthesis might be replaced by geothermal energy harvesting or chemical-based metabolisms. Biochemistry might diverge from carbon-centric pathways, possibly employing silicon or exotic compounds. Microbial life could thrive in deep oceans or subterranean refuges, enduring radiation levels that would obliterate ordinary Earth organisms. Intelligent life, if it arose, might perceive time, communication, and social structures in ways utterly alien to us, evolving strategies for survival in environments with no consistent sunlight and constant stellar threats. These considerations illustrate not only the resilience and adaptability of life, but also the vast diversity of possibilities in the universe. The stars, especially red dwarfs like Wolf 359, serve as laboratories of imagination, prompting us to reimagine what life might be, how it might endure, and how it might flourish under conditions we cannot fully replicate on Earth. While Wolf 359 is not an immediate hazard to our planet, it stands as a testament to the cosmic forces that shape the evolution of matter, energy, and potentially life itself. Gazing at such stars, we are reminded that the universe is both gentle and mercurial, capable of nurturing life in unexpected ways while simultaneously presenting profound challenges. In contemplating the extremes of habitability and survival, we deepen not only our understanding of the cosmos, but also our appreciation for the fragile, delicate balance that sustains life on our own world. However, the universe is rarely so straightforward, and the picture of life around red dwarfs is both fascinating and profoundly alien to our earthbound imagination. Imagine a world bathed not in the bright, familiar light of a yellow sun, but in the muted, persistent crimson glow of a red dwarf. The planets circling these stars would experience a rhythm of existence completely unlike anything on Earth, shaped by the dim light, slow stellar heartbeat, and unpredictable temper of their host star. Life, if it exists there at all, would be sculpted by these pressures, evolving in ways we can barely conceive. In the oceans of a distant water world, microbial life might cling to survival in shadowy depths, thriving in hidden thermal vents or under ice-covered seas where sunlight barely penetrates. On tidally locked planets, worlds where one side eternally faces the star while the other languishes in endless night, complex life might emerge in a narrow twilight strip between fire and frost. It is a precarious existence, one where every adaptation matters, where evolution is a constant negotiation with extremes. The potential for life is there, lurking just beyond the reach of our telescopes, waiting for our ingenuity to reveal it. This raises a compelling question. Could such life ever bridge the cosmic distances to reach us, or are these worlds forever isolated in their own stellar neighborhoods? The universe is vast, and the spaces between stars immense. Even if life flourishes around a red dwarf, it may remain forever invisible to us, existing as a parallel narrative, unfolding silently under the ruby glow of a distant sky. To understand just how alien these worlds might be, consider our own star, the Sun. A G-type main sequence star, our Sun is neither excessively hot nor cold, neither massive nor diminutive. Its steady output has allowed life on Earth to flourish for billions of years, a rare and fortunate balance. By contrast, red dwarfs, like the one at the heart of Wolf 359, are smaller, cooler, and faint by comparison. They emit only a fraction of the energy of our Sun, yet they dominate the galactic census. Nearly 70% of the stars in the Milky Way are red dwarfs, making them ubiquitous neighbors in our cosmic community. Red dwarfs are remarkable in their longevity. While the Sun has an expected lifespan of about 10 billion years, of which approximately 4.5 billion have passed, red dwarfs can burn steadily for tens, even hundreds of billions of years. They are the cosmic tortoises, slow and enduring, offering theoretically vast stretches of time for life to evolve. But this longevity comes at a price. A red dwarf's energy output is feeble, its warmth weak and uneven. Life orbiting such a star must contend with conditions drastically different from the gentle cycles of Earth's days and nights. One of the most striking challenges is tidal locking. A planet orbiting close enough to a red dwarf to remain within the habitable zone would likely rotate in such a way that one hemisphere perpetually faces the star, basking in dim red daylight, while the other plunges into eternal darkness. The extremes of temperature, the unyielding divide between fire and ice, would demand extraordinary resilience from any life that tries to survive there. Evolution would favor the hardy, the adaptable, the innovative. Life, if it exists, would likely be unlike anything familiar, a mosaic of strategies honed to endure constant stress. Red dwarfs also possess a volatile temperament. Our Sun emits solar flares, bursts of charged particles, but they are relatively moderate and intermittent, tempered by Earth's protective magnetic field and thick atmosphere. Red dwarfs, however, can erupt violently, showering their planets with frequent, intense radiation. A planet in such an environment faces a constant assault, its atmosphere vulnerable, its surface harsh and unforgiving. Any life that emerges must contend with this relentless challenge, evolving defenses against radiation, finding refuge in oceans, caves, or beneath protective layers of soil or ice. Photosynthesis, the engine of earthly life, becomes a daunting task under a red dwarf. Plants on our world harvest sunlight efficiently, converting it into the chemical energy that fuels ecosystems. But on a dimly lit red dwarf planet, sunlight is weaker, redder, and less abundant. Could life evolve entirely new mechanisms to capture energy, perhaps tapping geothermal heat, chemical reactions, or other forms of energy we cannot yet imagine? Complex ecosystems may be possible, but they would rely on novel solutions, reinventing the fundamental rules of life as we know it. In many ways, Earth is a lucky experiment in cosmic circumstances. The sun's energy is well balanced, its stability remarkable, and its position in the galaxy just right, far from the chaos of the galactic core, yet not too distant from the fertile, matter-rich regions needed for planet formation. Red dwarfs, for all their numerical superiority, present a more challenging canvas. While they offer the possibility of an extraordinarily long-lived environment, they impose severe constraints on temperature, radiation exposure, and planetary rotation, demanding extraordinary adaptation for life to take hold. Yet, perhaps therein lies the intrigue. Red dwarfs may host life forms entirely alien to our understanding, resilient and strange, thriving in twilight and darkness in ways that expand the very definition of life. They may be rare cradles of evolution in the truest sense, not just survival, but the invention of entirely new strategies for enduring the universe. Though planets around these stars are more common than those like Earth, their story is complex, abundant yet harsh, promising in longevity yet demanding in conditions, a stark counterpoint to the comfortable cradle of a G-type star. In the grand tapestry of the Milky Way, red dwarfs are the quiet, enduring witnesses to cosmic history, their planets potential havens for life that has adapted to extremes. They remind us that life's persistence is not always gentle, and that the universe can nurture existence in forms both alien and resilient. Our quest to understand these worlds is only beginning, and the potential discoveries awaiting us under the dim glow of distant red dwarfs may forever change our perspective on what it means to live, to survive, and to thrive in the cosmos. However, the universe is rarely so straightforward, and the picture of life around red dwarfs is both fascinating and profoundly alien to our earthbound imagination. Imagine a world bathed not in the bright, familiar light of a yellow sun, but in the muted, persistent crimson glow of a red dwarf. The planets circling these stars would experience a rhythm of existence completely unlike anything on Earth, shaped by the dim light, slow stellar heartbeat, and unpredictable temper of their host star. Life, if it exists there at all, would be sculpted by these pressures, evolving in ways we can barely conceive. In the oceans of a distant water world, microbial life might cling to survival in shadowy depths, thriving in hidden thermal vents or under ice-covered seas where sunlight barely penetrates. On tidally locked planets, worlds where one side eternally faces the star while the other languishes in endless night, complex life might emerge in a narrow twilight strip between fire and frost. It is a precarious existence, one where every adaptation matters, where evolution is a constant negotiation with extremes. The potential for life is there, lurking just beyond the reach of our telescopes, waiting for our ingenuity to reveal it. This raises a compelling question. Could such life ever bridge the cosmic distances to reach us? Or are these worlds forever isolated in their own stellar neighborhoods? The universe is vast, and the spaces between stars immense. Even if life flourishes around a red dwarf, it may remain forever invisible to us, existing as a parallel narrative, unfolding silently under the ruby glow of a distant sky. To understand just how alien these worlds might be, consider our own star, the Sun. A G-type main sequence star, our Sun is neither excessively hot nor cold, neither massive nor diminutive. Its steady output has allowed life on Earth to flourish for billions of years, a rare and fortunate balance. By contrast, red dwarfs, like the one at the heart of Wolf 359, are smaller, cooler, and faint by comparison. They emit only a fraction of the energy of our Sun, yet they dominate the galactic census. Nearly 70% of the stars in the Milky Way are red dwarfs, making them ubiquitous neighbors in our cosmic community. Red dwarfs are remarkable in their longevity. While the Sun has an expected lifespan of about 10 billion years, of which approximately 4.5 billion have passed, red dwarfs can burn steadily for tens, even hundreds of billions of years. They are the cosmic tortoises, slow and enduring, offering theoretically vast stretches of time for life to evolve. But this longevity comes at a price. A red dwarf's energy output is feeble, its warmth weak and uneven. Life orbiting such a star must contend with conditions drastically different from the gentle cycles of Earth's days and nights. One of the most striking challenges is tidal locking. A planet orbiting close enough to a red dwarf to remain within the habitable zone would likely rotate in such a way that one hemisphere perpetually faces the star, basking in dim red daylight, while the other plunges into eternal darkness. The extremes of temperature, the unyielding divide between fire and ice, would demand extraordinary resilience from any life that tries to survive there. Evolution would favor the hardy, the adaptable, the innovative. Life, if it exists, would likely be unlike anything familiar, a mosaic of strategies honed to endure constant stress. Red dwarfs also possess a volatile temperament. Our sun emits solar flares, bursts of charged particles, but they are relatively moderate and intermittent, tempered by Earth's protective magnetic field and thick atmosphere. Red dwarfs, however, can erupt violently, showering their planets with frequent, intense radiation. A planet in such an environment faces a constant assault, its atmosphere vulnerable, its surface harsh and unforgiving. Any life that emerges must contend with this relentless challenge, evolving defenses against radiation, finding refuge in oceans, caves, or beneath protective layers of soil or ice. Photosynthesis, the engine of earthly life, becomes a daunting task under a red dwarf. Plants on our world harvest sunlight efficiently, converting it into the chemical energy that fuels ecosystems. But on a dimly lit red dwarf planet, sunlight is weaker, redder, and less abundant. Could life evolve entirely new mechanisms to capture energy, perhaps tapping geothermal heat, chemical reactions, or other forms of energy we cannot yet imagine? Complex ecosystems may be possible, but they would rely on novel solutions, reinventing the fundamental rules of life as we know it. In many ways, Earth is a lucky experiment in cosmic circumstances. The sun's energy is well balanced, its stability remarkable, and its position in the galaxy just right, far from the chaos of the galactic core, yet not too distant from the fertile, matter-rich regions needed for planet formation. Red dwarfs, for all their numerical superiority, present a more challenging canvas. While they offer the possibility of an extraordinarily long-lived environment, they impose severe constraints on temperature, radiation exposure, and planetary rotation, demanding extraordinary adaptation for life to take hold. Yet perhaps therein lies the intrigue. Red dwarfs may host life forms entirely alien to our understanding, resilient and strange, thriving in twilight and darkness in ways that expand the very definition of life. They may be rare cradles of evolution in the truest sense, not just survival, but the invention of entirely new strategies for enduring the universe. Though planets around these stars are more common than those like Earth, their story is complex, abundant yet harsh, promising in longevity yet demanding in conditions, a stark counterpoint to the comfortable cradle of a G-type star. In the grand tapestry of the Milky Way, red dwarfs are the quiet, enduring witnesses to cosmic history, their planets potential havens for life that has adapted to extremes. They remind us that life's persistence is not always gentle, and that the universe can nurture existence in forms both alien and resilient. Our quest to understand these worlds is only beginning, and the potential discoveries awaiting us under the dim glow of distant red dwarfs may forever change our perspective on what it means to live, to survive, and to thrive in the cosmos. However, the story of life around red dwarfs is far more intricate than a simple comparison to our sun. Imagine a world bathed not in the familiar, bright yellow light of a G-type star, but in the muted, persistent crimson glow of a red dwarf. The rhythm of existence on such planets would be unlike anything we know, dictated by dim light, slow stellar beats, and unpredictable stellar flares. Life here, if it exists at all, would evolve under these pressures, shaping organisms in forms almost unimaginable to us. In hidden oceans of distant water worlds, microscopic life could cling to survival, dwelling in shadowed depths or around thermal vents where sunlight barely reaches. On tidally locked planets, where one side is eternally illuminated and the other trapped in perpetual night, complex life might find refuge in the narrow twilight zone between fire and frost, a precarious band where day and night coexist in an uneasy balance. Evolution in such conditions would be relentless, favoring only the most adaptable and resilient. The potential for life exists, waiting quietly, its presence hidden from our telescopes and instruments. This begs a profound question. Could life in these distant alien environments ever bridge the vast cosmic gulf to encounter us? Or are these worlds forever isolated in their own stellar neighborhoods, separated by unimaginable distances in cosmic time? Even if life thrives around a red dwarf, it may remain an invisible parallel story, unfolding silently under the soft ruby light of its star. To grasp the magnitude of these differences, consider our Sun, a middle-aged G-type main sequence star. Its output is steady and balanced, neither too hot nor too cold, allowing life to flourish on Earth for billions of years. In stark contrast, red dwarfs, such as Wolf 359, are smaller, cooler, and emit only a fraction of the Sun's energy. Yet they dominate the galaxy. Nearly 70% of the Milky Way's stars are red dwarfs, making them the silent majority of the cosmic neighborhood. Red dwarfs are astonishingly long-lived. While the Sun's lifespan is about 10 billion years, red dwarfs can burn for tens or even hundreds of billions of years. They are the universe's tortoises, enduring slow and steady. However, this longevity comes at a cost. Their energy output is weak, and planets within their habitable zones must orbit very close, often resulting in tidal locking. One side of such a planet basks in constant red light while the other languishes in eternal darkness, a condition that would challenge even the hardiest forms of life. Moreover, red dwarfs are notoriously volatile. While our Sun emits occasional flares, red dwarfs unleash frequent and powerful bursts of radiation. These stellar tempests could strip atmospheres, scorch surfaces, and threaten emerging life. Any organisms here would need extraordinary resilience, perhaps living deep underground, beneath oceans, or within thick protective layers of ice or soil. Even the process of photosynthesis would be fundamentally different. On Earth, plants convert sunlight into chemical energy efficiently, but on a dim red dwarf planet, life would need to harness the weaker red light or seek alternative energy sources such as geothermal heat or chemical processes. Complex life may emerge, but only by rewriting the rules that govern energy and survival. Earth, in comparison, appears extraordinarily fortunate. The Sun's energy is perfectly balanced, its stability remarkable, and its galactic position ideal, far enough from the chaos of the galactic core, yet close enough to fertile regions for planet formation. Red dwarfs, despite their abundance, offer a harsher environment, long-lived but low energy, irradiated, and often tidally locked. Life around these stars would be exotic, resilient, and adapted to extremes we can scarcely imagine. Yet that is precisely the allure. Red dwarfs may harbor life forms entirely alien to us, thriving under twilight and darkness, demonstrating the versatility and tenacity of life in the cosmos. While planets around red dwarfs are common, they are less hospitable by earthly standards. Still, they could host evolution that is slow, subtle, and extraordinarily innovative. In the grand tapestry of the Milky Way, red dwarfs are enduring sentinels of time, their planets silent witnesses to cosmic history. They reveal that life can persist not only in comfort but in extremes, reminding us that the universe's creativity extends far beyond familiar earthly forms. As we peer into the dim glow of distant red dwarfs, we may one day uncover life that challenges our very understanding of survival, adaptation, and the astonishing diversity of existence in the cosmos. One of the most captivating features of Wolf 359 is its magnetic field, a phenomenon that, while common in stars, reveals an extraordinary complexity in this seemingly small red dwarf. Much like Earth's magnetic field shields our planet from dangerous solar radiation, the magnetic field of Wolf 359 plays a pivotal role in shaping the environment around it, but with intensity and drama far beyond what we experience at home. Unlike the Sun, whose magnetic behavior we are somewhat familiar with, Wolf 359 exhibits a magnetic dynamism that is remarkable for a star of its size. Its field is in constant flux, generating flares and storms so powerful that they illuminate the underlying mechanisms of stellar magnetism on a scale both accessible and instructive to astronomers. At the heart of this magnetic activity lies a process known as magnetic reconnection. Here, magnetic field lines, drawn from different regions of the star, suddenly snap apart and reconnect in a spectacular release of energy. These reconnection events are the engine behind the star's flares, sudden bursts of radiation and particles that occur with a frequency and intensity that dwarfs anything the Sun produces. Each flare is a window into the inner workings of the star, offering scientists a chance to observe the physics of magnetic fields in action. By studying Wolf 359's flares, researchers can refine their understanding of how stars generate, sustain, and manipulate these invisible but potent forces. Moreover, the star's activity sheds light on the complex interactions between stellar magnetic fields and their surrounding space environments, a subject with profound implications for our understanding of stars across the galaxy. Wolf 359's significance extends far beyond its magnetic personality. As a low-mass red dwarf, it provides a natural laboratory for exploring stellar evolution in a category of stars that is often overlooked. Red dwarfs are stellar survivors, quietly burning hydrogen into helium over timescales that stretch into trillions of years, far exceeding the life expectancy of more massive stars like our Sun. Unlike their larger counterparts, these stars do not experience dramatic expansions, violent collapses, or explosive deaths. Instead, they follow a long, steady path along the main sequence, slowly radiating energy over epochs that dwarf human comprehension. Studying Wolf 359 allows astrophysicists to test and refine models of stellar evolution for low-mass stars, offering insights into how such stars persist for eons, and what fate ultimately awaits them when their hydrogen supply finally runs out. Each observation, each data point from Wolf 359 helps complete a broader cosmic puzzle, one that stretches from the faintest twinkle in the night sky to the overarching life cycle of galaxies themselves. Peering into the life of a star like Wolf 359 is no simple task, given its distance and modest brightness. Yet astronomers have developed ingenious techniques to probe its nature, chief among them spectroscopy. By dispersing the star's light into its constituent colors, much like a prism creating a rainbow, scientists can decode the chemical composition, temperature, and other fundamental properties of the star. Wolf 359 reveals itself as a composition primarily of hydrogen and helium, with trace amounts of heavier elements such as carbon and oxygen. These elemental fingerprints are more than just a chemical snapshot. They are indicators of the nuclear reactions fueling the star's core, the energy it radiates, and its evolutionary stage. Spectroscopic analysis also allows researchers to estimate the star's mass and age, offering a comprehensive view of a quiet yet complex stellar entity that, despite its faint appearance, carries a wealth of astronomical information. Understanding stars like Wolf 359 is crucial for grasping the broader population of the Milky Way. While our Sun is the star we know best, it is far from typical. In fact, red dwarfs dominate the galactic landscape, accounting for roughly 70 to 80% of all stars in our galaxy. These diminutive stars quietly maintain the structural and energetic backbone of the Milky Way, burning steadily while larger, more luminous stars steal the spotlight. By studying Wolf 359 and its peers, scientists can build more accurate models of stellar populations, estimating the average lifespan of stars, the types of planets that might orbit these low-mass stars, and even assessing the potential for life in their comparatively dim habitable zones. Each data point contributes to a larger understanding of galactic architecture, helping researchers map not only the distribution of stars, but also the intricate dance of energy, matter, and planetary systems that define the Milky Way. Wolf 359 holds particular significance because of its proximity to Earth. As one of the closest red dwarfs, it offers an unparalleled opportunity to study a star smaller and cooler than our Sun in great detail. Observing it is like glimpsing the quiet life of a cosmic neighbor, modest in luminosity, but profound in its implications for understanding the galaxy. Each flare, each spectroscopic signal, each subtle shift in brightness tells a story of stellar endurance and magnetic complexity, a story that has ramifications for our understanding of stars far and wide. The future of research on Wolf 359 and its red dwarf brethren is promising. With the advent of next-generation telescopes, astronomers are poised to investigate these stars with unprecedented clarity. Instruments such as the James Webb Space Telescope are set to provide detailed infrared observations, essential for studying cool, dim stars like Wolf 359. These new perspectives will illuminate previously hidden aspects of stellar atmospheres, magnetic fields, and dynamic activity, revealing layers of detail that may fundamentally reshape our understanding of how low-mass stars live, interact with their surroundings, and evolve over trillions of years. In essence, Wolf 359 is not just a faint point of light in the night sky. It is a living laboratory, a key to the past, present, and future of stars, and a testament to the subtle yet profound forces that govern our universe. Additionally, as telescopes and observational technologies continue to advance at an astonishing pace, the prospect of directly observing planets orbiting stars like Wolf 359 moves from the realm of imagination into the realm of scientific plausibility. While, to date, Wolf 359 has no confirmed exoplanets, the tantalizing possibility of discovering worlds circling such a star has astronomers on the edge of their seats. Red dwarfs, the class of stars to which Wolf 359 belongs, have long been considered prime candidates for hosting planets within their habitable zones, the delicate regions where temperatures could allow liquid water to persist on a planet's surface. Water, as every astrobiologist will tell you, is an indispensable ingredient for life as we understand it. The discovery of planets around Wolf 359 could provide a profound glimpse into the potential for life in the universe. Life that exists not in the comforting warmth of a sun like ours, but under the dim, persistent glow of a red dwarf star. Worlds bathed in an unfamiliar, muted light. So what have we truly learned from Wolf 359, a star so modest in appearance that it might easily be overlooked in the night sky? Despite its unassuming presence, Wolf 359 has earned its place as a key figure in astrophysical studies. Its magnetic activity offers insight into the mechanisms that govern stellar behavior, while its characteristics feed into broader models of stellar evolution and enhance our understanding of the chemical composition of stars. Far from being a static, unchanging point of light, Wolf 359 continues to educate and surprise scientists, reminding us that even the faintest stars can hold immense significance. Picture a calm, moonless night. You stand alone beneath a vast, star-studded sky, each pinprick of light seemingly steady and eternal. Most stars appear tranquil, serene, and distant. Yet, among them, some stars conceal a far more volatile existence. Imagine if one of those tiny points suddenly erupted in a brilliant, blinding flash, like releasing energy so intense that even the most dazzling fireworks on Earth would pale in comparison. This is the nature of flare stars, and it is the reason Wolf 359, despite its modest size and faint luminosity, has captivated astronomers for decades. Wolf 359 is not just any red dwarf. It is a flare star, a category of stars that, although small and low in mass, can unpredictably release colossal bursts of energy in the form of stellar flares. These flares are nothing like the gentle twinkling we casually admire from our vantage point on Earth. They are violent, explosive outbursts of energy and radiation, the kind that can send ripples of charged particles surging through space. The secret behind these dramatic stellar tantrums lies in the star's magnetic field. Unlike the relatively calm and steady magnetic fields we experience on Earth, a flare star's magnetic field is a tumultuous and dynamic force, constantly shifting, reconnecting, and writhing within the star's atmosphere. In stars like Wolf 359, this magnetic turbulence reaches extremes. Twisted loops of magnetic flux build tension like a coiled spring, accumulating vast reserves of energy over time. Eventually, the tension becomes unsustainable, and the magnetic lines snap or rearrange in a spectacular magnetic reconnection, unleashing their pent-up energy in a radiant burst, an event we observe as a flare. Visualize stretching a rubber band to its breaking point and then releasing it. The sudden snap releases stored energy instantly, a small-scale analog to the immense forces at play in a flare. In Wolf 359, these flares can dwarf anything the sun produces, releasing energy equivalent to thousands of times the total output of the sun's surface in brief, brilliant flashes. The star's flares are a window into extreme stellar physics, offering astronomers a natural laboratory to study the most violent conditions possible within a star's atmosphere. To understand these stellar eruptions more intimately, consider the plasma, the superheated electrically charged gas that swirls in chaotic patterns in the outer layers of Wolf 359. Magnetic field lines twist and knot within this plasma, storing enormous amounts of energy like tightly wound springs. When the pressure becomes unbearable, the magnetic lines reconnect, ejecting plasma and radiation outward in a sudden flare. Even from our distant vantage point on Earth, we witness only a fraction of the energy released in these cosmic outbursts, a reminder of the staggering scale of processes occurring light years away. The consequences of these flares extend beyond mere spectacle. For any planets orbiting close to Wolf 359, these violent eruptions could be perilous. The high energy particles and intense radiation from a flare are more than a scientific curiosity. They are potential hazards. A nearby planet could endure radiation bursts capable of stripping away its atmosphere, leaving its surface exposed to the harsh vacuum of space. Yet distance is crucial. A planet far enough from the star might survive unscathed, while one too close could face catastrophic consequences. The delicate interplay of distance, energy, and timing determines whether a planet could harbor life, be scorched, or be rendered entirely uninhabitable. You might ask, isn't our sun a flare star too? It is. But the comparison only goes so far. The sun's flares are relatively mild, infrequent, and far less intense than those of flare stars like Wolf 359. The frequency, magnitude, and unpredictability of Wolf 359's eruptions are what set it apart. Each flare represents a window into the star's extraordinary magnetic vigor, revealing phenomena that challenge and expand our understanding of stellar physics. Wolf 359, a modest red dwarf nestled quietly in the constellation Leo, may seem unremarkable at first glance, yet it embodies the drama and intensity that lie hidden in the universe's smaller stars. Every flare is a reminder that even the dimmest lights in our sky can be sites of immense power, each one a story of magnetic tension, explosive release, and the dynamic forces shaping the cosmos. Through its subtle glow and sudden brilliance, Wolf 359 continues to draw astronomers closer, inviting humanity to witness, measure, and ultimately understand the astonishing complexity of our stellar neighbors. Furthermore, when we examine the behavior of stellar flares, we find a fascinating contrast between our Sun and certain smaller, more volatile stars. Solar flares on the Sun are typically constrained to the uppermost layers of its atmosphere, rippling across its surface in bursts of energy that, while intense, rarely penetrate deeply into its structure. In stark contrast, stars like Wolf 359, tiny, fiery red dwarfs, can produce flares that extend far deeper into their atmospheric layers. These flares unleash energy on a scale that dwarfs what we experience from our Sun, creating conditions that are both extraordinary and hazardous. This profound difference makes flare stars such as Wolf 359 a treasure trove for scientists investigating stellar activity. They offer a live laboratory for studying what occurs when a star's magnetic field is pushed into overdrive, a phenomenon that is as violent as it is illuminating. Now, let us return to our thought experiment. Picture a planet caught in orbit around a star like Wolf 359. Could the energy released by one of its powerful flares be enough to strip away the planet's protective atmosphere, leaving it barren and lifeless? The answer is nuanced. While the flares are undeniably potent, the planet's distance from the star becomes a critical factor. If a planet resides within the so-called habitable zone, the region where temperatures might allow liquid water to exist on its surface, it could find itself particularly vulnerable. Intense radiation bursts could slowly erode its atmosphere, making survival for any nascent life forms precarious. Conversely, a planet situated farther from the star would experience a significant weakening of the flare's energy by the time it reaches its surface, enhancing its chances of retaining an atmosphere capable of supporting life. In essence, flare activity alone cannot fully determine a planet's fate. The interplay of stellar type, flare intensity, and orbital distance all coalesce to shape the potential for life. As astronomers continue to probe the cosmos, flare stars like Wolf 359 have emerged as a particularly captivating focus. Technological advancements have allowed scientists to observe these distant stars with unprecedented clarity, revealing not only the magnitude and frequency of their flares, but also the profound impact these events could have on orbiting worlds. Understanding the nature of these flares is increasingly vital as humanity searches for planets that might harbor life. In this context, Wolf 359 and similar red dwarfs become more than mere points of light in the night sky. They are laboratories for the possibilities and perils of life beyond our solar system. When imagining the search for extraterrestrial life, the mind often conjures verdant worlds orbiting sun-like stars, idyllic planets teeming with flora, fauna, and potentially intelligent civilizations. But consider this, one of the most intriguing prospects for life might lie around a star utterly unlike our own. Could a faint, diminutive red dwarf such as Wolf 359 support life, perhaps even intelligent life? Surprisingly, some scientists argue that it could. Red dwarfs are not only the most numerous stars in our galaxy, but they also possess characteristics that make them uniquely interesting for the study of extraterrestrial life. These small, cool, and unassuming stars outnumber stars like the Sun by a substantial margin, accounting for approximately 70 to 80% of all stars in the Milky Way. Despite their modest size and luminosity, red dwarfs are remarkably long-lived, burning their nuclear fuel at a slow pace that allows them to shine steadily for tens to hundreds of billions of years, far outlasting stars like our Sun, which will exhaust its fuel in just a few billion years. This extraordinary longevity has profound implications for the potential development of life. A planet orbiting a red dwarf might have vastly more time to foster life, and perhaps even intelligent life, than a planet orbiting a star like the Sun. Yet the challenges are formidable. Red dwarfs emit far less light than our Sun. Wolf 359, for instance, shines with only about 15% of the Sun's brightness. Consequently, any planet within the habitable zone would need to orbit very closely to capture sufficient warmth, placing it at significant risk from the star's frequent and intense flares. These stellar outbursts could strip away atmospheres and subject the surface to deadly radiation, demanding that life, if it exists, be extraordinarily resilient. Imagine, then, life that adapts to a dim, reddish environment where the usual processes of photosynthesis might give way to alternative energy strategies, such as chemical energy or geothermal heat. The organisms on such a world would be shaped by necessity, evolving under the relentless influence of their star's erratic temperament. And if life were to reach intelligence on such a planet, it might develop technology radically different from our own, engineered to withstand constant radiation and disrupted communications. Civilizations in such systems could build underground cities, create sophisticated shielding systems, and employ advanced communication methods beyond the interference of solar flares. The very nature of their environment would drive ingenuity and resilience in ways almost unimaginable to us. This line of thinking naturally intersects with the Fermi paradox. If the universe is vast and replete with potentially habitable worlds, why have we detected no signs of intelligent life? Perhaps red dwarfs, like Wolf 359, hold part of the answer. Life around these stars, if it exists, might be alien in ways that render it unrecognizable or undetectable with our current methods. Civilizations might be isolated by environmental constraints, or might communicate through channels we cannot perceive, leaving the cosmos seemingly silent. On the other hand, it is possible that red dwarfs are simply inhospitable to advanced life, steering our expectations away from the true conditions required for intelligence to flourish. Detecting such life presents its own set of challenges. The persistent flares and radiation emissions of red dwarfs would make long-distance communication extraordinarily difficult. Even subtle signals could be scattered or obliterated, further complicating the search for extraterrestrial intelligence. Yet, the sheer number of red dwarfs in our galaxy keeps hope alive. If life can adapt to these extreme conditions, it might be far more widespread than previously imagined. As scientists refine methods for discovering exoplanets and detecting potential biosignatures, the dream of finding life around stars like Wolf 359 remains tantalizingly within reach. Stars, often perceived as fixed points of light, are in fact dynamic, ever-moving entities. Wolf 359, one of the closest stars to our Sun, traverses the galaxy at a remarkable pace, approximately 28 kilometers per second. While this may seem modest on a cosmic scale, it underscores the restless nature of stars as they navigate the gravitational currents of the Milky Way. Observing them is to witness a vast, intricate dance, a reminder that the universe is not static, but in constant motion, shaping the cosmic landscape with each passing millisecond. In exploring stars like Wolf 359, we are not merely cataloging distant lights in the sky. We are engaging with a living, shifting universe, probing the limits of what life could endure, imagining civilizations thriving under alien suns, and contemplating the mysteries of our cosmic neighborhood. Every flare, every orbiting planet, every burst of radiation tells a story of possibility, resilience, and the endless complexity of the cosmos, a story that is only beginning to unfold before our eyes. However, its journey through the cosmos is far from insignificant. Wolf 3359, though moving at a relatively modest pace, is steadily charting a course through our local galactic neighborhood, gradually weaving through regions of the Milky Way that, in the unimaginably distant future, may bring it closer to our own solar system. To put its motion in perspective, consider the Sun. It races around the galaxy at an astonishing speed of about 220 kilometers per second, yet it occupies a position far from the galactic center. In contrast, Wolf 359 resides much nearer to us, making it one of the more immediate stellar neighbors worthy of attention. While its velocity is only a fraction of the Sun's, its proximity transforms it from a distant, abstract point of light into a tangible subject of astronomical inquiry. This combination of low speed and closeness makes Wolf 359 an extraordinary natural laboratory for scientists. Its movement, what astronomers call proper motion, offers critical insight into the mechanics of stars in our corner of the galaxy. Stars are never static. They drift, shift, and alter their relative positions over time. By observing Wolf 359, researchers can track how a star's journey shapes the dynamics of its surrounding stellar environment. Despite its gradual pace, Wolf 359's proper motion is substantial enough that over thousands of years, its position in the night sky will noticeably change. While this shift may be imperceptible to humans on short timescales, it provides astronomers with a wealth of information about the star's trajectory and the gravitational forces acting upon it. Looking ahead, what might happen if Wolf 359 continues along its current path? Remarkably, it will indeed come closer to us, though not for millions of years. Projections suggest that in approximately 7,800,000 years, Wolf 359 will make its nearest approach to the solar system, arriving at a distance just under 8 light years. While still comfortably far away, this represents a significant reduction from its current separation. In the grand scheme of cosmic time, this is but a fleeting moment. Though there is no danger of Wolf 359 intruding into our solar system, its passage raises intriguing possibilities. The Earth itself would likely remain unaffected, as space is vast and sparsely populated, even in the neighborhood of stars. Yet, imagine a future in which humanity has spread among the stars, venturing into interstellar space. Wolf 359 could become a tantalizing destination for exploration, an opportunity to study one of our closest stellar neighbors firsthand. Over immense timescales, the star's motion may also intersect with other stars, resulting in what astronomers call stellar flybys. These encounters, rare but impactful, could subtly influence the orbits of nearby planets or even gravitationally nudge a star out of its local environment. Such events, while extraordinary in their scale and rarity, contribute to the ever-shifting architecture of our galaxy. To comprehend the far-reaching effects of Wolf 359's movement, astronomers employ sophisticated computer simulations that model the future trajectories of stars. These simulations integrate gravitational interactions, stellar motions, and other cosmic forces, effectively allowing scientists to watch a star's journey unfold across millions of years. In Wolf 359's case, the models reveal a path that threads through the galaxy like a carefully plotted interstellar road trip. While the destination is distant and abstract, the journey itself offers endless possibilities for discovery. These predictive tools illuminate how local star systems may evolve, whether by close encounters, subtle deflections, or broader galactic influences. Although the motion of a single star may seem distant or abstract, it is a fundamental piece in the grand puzzle of cosmic dynamics. Stars like Wolf 359 demonstrate that the galaxy is a constantly shifting, interlinked system, where even modest movements ripple outward, shaping neighbors and contributing to the broader evolution of our universe. Observing these motions deepens our understanding of the forces sculpting our cosmic environment and reminds us that the stars are not eternal, fixed points, but active participants in a vast, ongoing celestial dance. Now consider the extraordinary implications if Earth were not warmed by a bright yellow sun, but instead orbited a small, dim red dwarf like Wolf 359. The thought provokes a cascade of questions about life, environment, and human evolution under such alien light. Red dwarfs, cool and faint compared to our sun, bathe their worlds in a soft crimson glow, dim but not devoid of possibility. These stars are remarkably common, constituting roughly 70 to 80% of the galaxy's population. While their modest energy output imposes new conditions, life may still find a way. On a planet illuminated by a red dwarf, Earth's climate would be cooler, its surface bathed in a perpetual twilight of muted red and amber hues. The sky itself might lose its familiar blue, replaced by a constant warm glow. Plants would adapt, perhaps evolving dark foliage, rich purples, or deep reds to maximize energy absorption from the dim light. Forests might appear black under this strange star, absorbing every photon available to sustain life. Ecosystems would seek balance, storing energy from alternative sources such as geothermal activity. Humans, too, would be transformed. Eyes adapted to low-light vision, skin tuned to capture scarce light, bodies attuned to irregular rhythms. If the planet were tidally locked, one hemisphere would face eternal daylight, the other perpetual darkness, reshaping societies, economies, and cultural patterns. Civilization might harness geothermal energy or solar power in unprecedented ways. The concept of time itself could change, with days stretching for weeks or months under slow-rising, languid sunsets. Such worlds illustrate the astonishing diversity of life-supporting conditions that might exist. The universe is not limited to planets orbiting stars like our sun. It is filled with possibilities. Life, if present, may thrive under the crimson glow of dim red dwarfs, adapting in ways beyond our current imagination. As astronomers search for habitable worlds, they must expand their vision to include these unlikely stellar hosts. Wolf 359 exemplifies the richness of our local cosmic neighborhood and hints at the broader variety of worlds that await discovery. Standing beneath the night sky, one can contemplate the quiet yet profound significance of stars like Wolf 359. Small, unassuming, and often overlooked, red dwarfs form the backbone of our galaxy, shaping the environment of countless other stars and planetary systems. They may be modest in size, but their influence is immense, quietly orchestrating the cosmic rhythm around them. Wolf 359, along with its fellow red dwarfs, reminds us that the galaxy's grand design is composed not only of dazzling giants, but also of these persistent, understated celestial neighbors, each playing its part in the endless story of the universe. And so, in the quiet depths of our galactic neighborhood, one star rises to subtle prominence: Proxima Centauri. Just over 4 light-years from our sun, it holds the distinction of being the closest known star to our solar system, a fact that immediately earns it a special place in the hearts of astronomers. But proximity is only part of Proxima's allure. This star has a planet orbiting in its habitable zone, a tantalizing hint that life, or at least the conditions for it, could exist on worlds circling these faint red suns. The possibility ignites the imagination. What might life around a red dwarf look like? Could these planets host ecosystems radically different from our own? Proxima Centauri is a lively neighbor. Its surface frequently bursts with solar flares and magnetic storms, painting a picture of a dynamic and ever-changing environment. Compared to Wolf 359, which burns quietly with measured consistency, Proxima's activity is a cosmic fireworks display. Yet, even with these eruptions, it is still faint, its light subdued when measured against the brilliance of our sun. Travel a little farther into the galaxy, about 6 light-years from Earth, and you encounter Barnard's star. At first glance, its subtle glow might deceive the observer. It seems to drift lazily through the cosmos. Yet in galactic terms, Barnard's star is a speedster, racing through our stellar neighborhood at a remarkable pace. It may lack the fame of Proxima Centauri, but its rapid motion tells an incredible story about gravitational forces and stellar dynamics, the invisible hands that guide stars on their trajectories through the Milky Way. Its light, like that of most red dwarfs, is modest and understated, a faint reddish pinprick against the vast blackness of space. Further out, at just shy of 11 light-years away, lies Ross 128, a quieter, more reserved member of this stellar family. Less active than Proxima and even more subdued than Wolf 359, it emits a gentle, almost meditative glow. Yet in its quietude, it shares all the hallmarks of red dwarfs: small size, low temperature, and astonishing stability. These characteristics, often overlooked in favor of brighter stars, make Ross 128 and its kin vital to understanding the universe at large. They are the steady, enduring heartbeat of our galaxy. Wolf 359 itself, nestled within this family of stars, embodies many of these same qualities. Slightly smaller than its neighbors, cooler and dimmer, it presents a contrast to the flaring unpredictability of Proxima Centauri. Burning steadily and calmly, Wolf 359 offers a model of cosmic reliability. Its mass is only a tenth that of our Sun, and its luminosity barely reaches 1/130th of the Sun's output. Yet for astronomers, its modest glow is significant, not because it shines brightly, but because it is representative of the countless red dwarfs that populate the Milky Way. Compared to Barnard's star, Wolf 359's motion through space is leisurely, almost contemplative. It does not race through the galaxy. It drifts, and therein lies part of its fascination: predictability in a universe often dominated by cataclysmic events and rapid transformations. The true marvel of Wolf 359 and of red dwarfs in general is their extraordinary longevity. Unlike massive stars which burn hot and die young in spectacular supernovae, red dwarfs consume their hydrogen with remarkable efficiency. Stars like Wolf 359 can continue to shine for billions, even trillions of years, vastly outliving stars such as our Sun, which has a projected lifespan of around 5 billion years. In the cosmic timeline, these stars are the enduring sentinels of the galaxy, illuminating the darkness steadily and reliably over epochs incomprehensible to human minds. Within the local stellar community, Wolf 359 and its companions belong to the M-class stars, the coolest and smallest stars in the stellar classification system. Though faint and unassuming to casual observers, M-class stars dominate the Milky Way in sheer numbers, forming the backbone of our local stellar environment. Proxima Centauri, Barnard's star, and Ross 128 all fall into this same category, quietly exerting their presence on the galactic neighborhood despite their lack of bright spectacle. When viewed on a local stellar map, a chart of all stars within roughly 20 light-years of our Sun, the dominance of these red dwarfs becomes apparent. The brightest and most energetic stars, like Alpha Centauri, are exceptions rather than the rule. Most of the Sun's immediate neighbors are diminutive, cool, and faint, their subtle light testifying to a quiet prevalence rather than dazzling display. Understanding Wolf 359 and similar stars is crucial not merely for cataloging purposes, but for the future of interstellar exploration. Red dwarfs, with their stable, long-lived natures, are ideal candidates for humanity's first ventures beyond our solar system. Proxima Centauri, at a mere 4.2 light-years away, is already being considered as a potential target for interstellar probes. Technology may one day allow spacecraft to travel to these distant worlds, to examine their planets, and perhaps to search for signs of life. The significance of these stars extends beyond exploration alone. Red dwarfs offer the conditions necessary for life to evolve on orbiting planets. With their extended lifespans, they provide ample time for complex ecosystems to emerge, potentially harboring civilizations entirely alien to our own. While Wolf 359 may seem insignificant in the vast cosmic expanse, its value is monumental, forming a foundational piece of a puzzle that could one day reveal the universe's greatest mysteries. Together, Wolf 359, Proxima Centauri, Barnard's star, Ross 128, and countless other red dwarfs create an intricate, interconnected web within our corner of the Milky Way. They illuminate not with blinding brilliance, but with enduring quiet light, offering humanity its first tangible footholds in the cosmos. They are the stepping stones to interstellar journeys, the initial beacons for voyages that might take centuries or millennia to realize, yet promise to reshape our understanding of life, existence, and the universe itself. When one imagines standing on a distant exoplanet, gazing up at a night sky dominated not by golden suns but by faint reddish points of light, the potential of these red dwarfs becomes tangible. Each one is a possible host for planets, a possible cradle for life, and a key to answering one of humanity's oldest questions: are we alone? Red dwarfs, unassuming yet overwhelmingly numerous, represent both a cosmic majority and an extraordinary opportunity. In their quiet persistence, they hold the promise of discovery, exploration, and perhaps the revelation of life beyond Earth. In contemplating Wolf 359 and its stellar family, it becomes clear that the universe is not solely composed of radiant giants. Instead, it is the unheralded, dim, enduring stars, the red dwarfs, that define our immediate galactic surroundings, guiding us toward the stars that might one day become humanity's first interstellar destinations. Their soft, steady glow is a reminder that even the quietest stars have stories to tell, that even the smallest neighbors may hold the keys to the universe itself. One of the most fascinating aspects of our search for life beyond Earth revolves around red dwarfs, tiny stars that at first glance might seem unremarkable compared to the bright, familiar glow of our sun. Yet, these small, dim stars have become the unsung heroes of exoplanet discovery, offering unique advantages that make them invaluable in our quest to find potentially habitable worlds. Their significance lies first in their size and luminosity. Unlike larger stars like our sun, red dwarfs burn more slowly and radiate less light. This has a profound effect on the planets that orbit them. A planet that could support life would need to hug its star closely, orbiting far nearer than Earth orbits the sun. While this might sound precarious, it is actually a boon for astronomers. Planets in such tight orbits cross in front of their stars more frequently and are easier to detect. Each orbit produces subtle dips in starlight, tiny flickers that serve as telltale signatures of a hidden world. And the story doesn't end there. These small stars lend themselves particularly well to a method called the transit technique. Picture a planet gliding across the face of its star, like a minuscule moth passing in front of a glowing lamp. From our vantage point across the vastness of space, the star's light dims ever so slightly during these moments, a signature that, when carefully analyzed, can reveal the planet's presence, size, and even hints about its atmosphere. Because red dwarfs emit less intense and more stable light than stars like our sun, these dips are more noticeable, making these stars prime targets for discovering Earth-sized exoplanets that might harbor life. In essence, red dwarfs act as cosmic magnifying glasses, bringing their orbiting worlds into sharper relief for our instruments. The importance of these stars was underscored by groundbreaking missions like the Kepler Space Telescope, and more recently, the Transiting Exoplanet Survey Satellite, or TESS. These missions transformed the hunt for exoplanets from a speculative endeavor into a systematic exploration, turning the cosmos into a sort of interstellar treasure map, with red dwarfs as the richest veins of potential. Kepler, by concentrating on a small swath of the sky, detected thousands of planets, many orbiting these cool, diminutive stars. Its discoveries revealed that some of the most promising candidates for life weren't circling bright, sun-like stars, but these unassuming red dwarfs. TESS has continued this work on a broader scale, scanning the entire sky and finding hundreds of candidate exoplanets, a majority of which also orbit M-class red dwarfs. With roughly 70% of the stars TESS observes falling into this category, astronomers are gaining an unprecedented understanding of the frequency of planets and the factors that make a world potentially habitable. Among the standout discoveries is Proxima b, a planet orbiting Proxima, the star nearest our sun, just over 4 light-years away. Situated in the habitable zone of its star, Proxima b presents tantalizing possibilities. If conditions are right, liquid water could exist on its surface, a prerequisite for life as we know it. Though much about the planet, its atmosphere, surface conditions, and actual capacity to sustain life remains unknown, its proximity and location alone make it a cornerstone in exoplanetary research. Similarly, the TRAPPIST-1 system has captivated scientists worldwide. A single ultra-cool red dwarf hosts 7 Earth-sized planets, 3 of which lie squarely in the habitable zone. The compact arrangement of these planets allows for comparative studies that could reveal the potential for life, atmospheric compositions, and the ways in which planets interact with their host star. However, this promising picture comes with significant caveats. Red dwarfs, especially younger ones, are notorious for stellar flares, sudden, intense bursts of radiation that could strip away planetary atmospheres and render a once promising world uninhabitable. Moreover, many planets orbiting these stars are tidally locked, presenting one eternal day side to the star while the other remains in perpetual darkness. Such conditions create extreme temperature gradients, challenging the adaptability of life as we understand it. The limitations of our detection methods add another layer of complexity. While the transit method is highly effective for planets that cross in front of their stars, from our perspective, it cannot reveal worlds that fail to align perfectly along our line of sight. Consequently, countless planets may remain hidden in plain sight, yet the horizon is brightening. Next-generation instruments promise to unlock deeper insights into these elusive worlds. The James Webb Space Telescope, with its unprecedented ability to probe exoplanet atmospheres, may provide the first concrete evidence of habitable conditions beyond our solar system. Advanced space-based interferometers could eventually image distant planets directly, scanning for chemical signatures that hint at biological activity. Every advancement brings us closer to addressing one of humanity's most profound questions. Are we alone in the universe? Even as we contemplate these distant worlds, it is remarkable to consider their relative proximity. Take Wolf 359, a red dwarf merely 7.9 light-years from Earth. In cosmic terms, this is practically our next-door neighbor. Yet, even this nearby star lies at a distance that stretches human imagination, nearly 47 trillion miles, or 76 trillion kilometers. Using our current technology, such as the Parker Solar Probe, the fastest spacecraft ever built, traveling at roughly 430,000 miles per hour, it would still take over 17,000 years to reach it. The scale is staggering, a humbling reminder of the vastness of space. But the sheer difficulty does not dampen the human spirit of exploration. Engineers and scientists are already envisioning ways to bridge these interstellar distances. From hypothetical nuclear propulsion systems to concepts like laser-powered light sails, the ideas being explored could, one day, make journeys to stars like Wolf 359 feasible. These ventures represent more than just technological ambition. They embody a curiosity that drives humanity to explore, to seek, and to understand. In studying red dwarfs and their planets, we are not just cataloging distant orbs of rock and gas. We are piecing together a map of potential homes, laboratories, and perhaps even the first hints of extraterrestrial life. In the end, red dwarfs, these seemingly insignificant pinpoints of light, may hold the answers to some of the greatest questions we can ask. They remind us that the universe often hides its most profound secrets in the most unassuming places. Each planet discovered, each flare observed, and each transit measured brings us one step closer to understanding our place in the cosmos. And as we continue to look upward, driven by curiosity and the relentless pursuit of knowledge, the humble red dwarfs scattered across our galaxy could well illuminate the path toward discovering life beyond our Earth, turning the unknown into a new frontier of possibility and wonder. One of the most tantalizing visions of interstellar exploration originates from Breakthrough Starshot, an ambitious initiative with the bold aim of sending tiny, ultralight spacecraft to the stars nearest to our own sun. Imagine, if you will, miniature star chips, slender wafers embedded with cameras and sensors, attached to delicate, reflective sails so thin they could almost be mistaken for a whisper of material. These sails, designed to harness the sheer force of light, are central to the project's revolutionary approach. The concept is elegant in its simplicity, yet staggering in its implications. By directing extraordinarily powerful lasers at these sails, the spacecraft could be accelerated to speeds approaching 1/5 the velocity of light, roughly 60,000 kilometers per second. At such a breakneck pace, a journey to Proxima Centauri, our closest stellar neighbor, could be completed in just over 2 decades. Even reaching Wolf 359, slightly farther afield, might be achieved in a mere 40 years, a fraction of the time conventional propulsion systems would require. It is an audacious idea that could transform humanity's relationship with the cosmos, a leap that turns interstellar travel from a centuries-long dream into a tangible, if challenging, endeavor. Yet, Breakthrough Starshot faces monumental hurdles. Engineers must develop lasers of unprecedented power and precision, capable of accelerating these frail star chips without vaporizing them. The spacecraft themselves must endure the brutal vacuum of space, the relentless radiation, and the potential collisions with stray particles moving at unimaginable speeds. Despite these formidable obstacles, the project embodies a vision of a future in which humans might touch the stars without leaving the realm of possibility behind. Now contrast this with a wholly different approach, the generation ship. Here the ambition shifts from speed to endurance. A generation ship is a vast, self-sustaining vessel, conceived to carry human life across the expanse of space for multiple generations. Unlike a brief, high-velocity voyage, a generational journey is a slow, continuous migration, where those who embark may never witness their destination. Their descendants would inherit the legacy of arrival. The challenges are staggering. Such a ship would need to house not only food, water, and oxygen, but also systems capable of recycling waste and maintaining environmental stability for potentially hundreds or thousands of years. Imagine a floating city, self-contained and in perpetual motion, reliant on intricate technology to sustain life indefinitely. But the barriers are not merely technical. Social cohesion, psychological well-being, and the motivation of successive generations pose profound questions. How does one maintain a thriving, purposeful society aboard a vessel where no individual will ever step onto alien soil? Even with our most optimistic projections of technological advancement, such journeys could stretch across centuries. Far from a simple expedition, the generation ship is an odyssey in the truest sense, more philosophical than practical in today's context. And then there's the dream of near light speed travel, a realm where the mathematics of motion become both thrilling and terrifying. Imagine a spacecraft traveling at 90 or 99% of the speed of light. At these extraordinary velocities, a trip to Wolf 359 could be completed in as little as 8 to 10 years from the perspective of the travelers on board. Yet relativity introduces its own complexities. Time itself bends in strange ways as velocity approaches light speed, a phenomenon known as time dilation. While astronauts might age only a handful of years during the voyage, the world they leave behind could see decades or even centuries pass before their return. The human cost of such journeys becomes philosophical as well as practical. Is the opportunity to traverse the stars worth the certainty that everything and everyone known on Earth could change or disappear in one's absence? This raises a crucial question. Why Wolf 359? While it is a scientifically fascinating red dwarf with potential planets, the sheer distance makes it a daunting target. Might there be closer, more hospitable systems worth our focus? Could resources directed toward reaching Wolf 359 be better spent exploring our own galaxy or safeguarding life on Earth? The answer may only come with the passage of time and with the evolution of our understanding, our technology, and our ambitions. Yet, even as we weigh practicality, the universe offers lessons in patience and longevity through stars themselves. Consider Wolf 359 not merely as a destination, but as a cosmic survivor. If we could fast forward time by trillions of years, the cosmos would appear stark and dim. Most stars, once brilliant and magnificent, would have long since exhausted their fuel and faded into cold remnants. Supernovas would be echoes of a bygone era, black holes slowly evaporating, galaxies dissolving. Amid this somber backdrop, Wolf 359 persists, a small, unassuming red dwarf burning faintly but steadily, outliving giants, civilizations, even entire galaxies. The secret of its endurance lies in its nature. Unlike massive stars that burn intensely and die young, red dwarfs are modest and patient. Wolf 359 contains less than 10% of the sun's mass and emits barely 1,000th of its brightness. Its slow, convective fusion stirs hydrogen from its outer layers into the core, ensuring that every particle contributes to energy generation. There is no waste, no rush, just quiet, efficient persistence. As a result, red dwarfs can shine for up to 10 trillion years, hundreds of times longer than the current age of the universe. They play the long game, and in doing so, become the last lights in a darkening cosmos. This makes Wolf 359 emblematic not just of endurance, but of the extraordinary power of the ordinary. While our sun and stars like it burn brightly and briefly, Wolf 359's unhurried existence allows it to persist far beyond the lifespan of galaxies, civilizations, and cosmic fireworks. Red dwarfs are abundant, yet none have yet reached the end of their life cycle. Each one is a living testament to patience, a reminder that in a universe obsessed with spectacle, quiet perseverance can endure beyond comprehension. Looking even further, one can imagine the far future universe, 100 trillion years from now, where galaxies have merged, star formation has ceased, and entropy dominates all. The cosmos is dim, sparse, and silent, yet Wolf 359 continues to glow, a tiny, steadfast beacon amidst the darkness. Eventually, it too will exhaust its hydrogen, fading quietly into a white dwarf, and then cooling to a black dwarf, a frozen relic. And even then, current physics suggests that the universe may not yet have aged enough for a single red dwarf to have completed this final transformation. Wolf 359, in its quiet persistence, offers a mirror to humanity's ambitions. Whether through solar sails, generational voyages, or near light speed travel, the dream of reaching the stars is a testament to our curiosity, our patience, and our willingness to confront the vast scales of space and time. One day, perhaps, humans will step across the gulf of interstellar distances and witness the humble, enduring glow of a red dwarf firsthand, a cosmic companion that has survived the eons with quiet dignity, reminding us that the universe rewards persistence, patience, and imagination in ways that are profound and eternal. And so Wolf 359 drifts quietly through the cosmic ocean like a diminutive red dwarf, whose unassuming presence masks a story that stretches across unimaginable spans of time. While our human eyes are drawn to the spectacular fireworks of massive stars, the brilliant supernovas, the sudden collapses, the galaxies lit ablaze by their ferocity, Wolf 359 tells a different story. It's a slow, patient narrative, a tale not of spectacle, but of endurance. It flickers faintly, almost imperceptibly, yet in that subtle glow lies a testament to persistence on a scale so vast that our minds can barely comprehend it. Humans are accustomed to the notion of endings. We age, we grow, and ultimately we fade. Our solar system itself, with all its planets and moons, its orbiting rocks and radiant sun, is only a temporary arrangement in the vast theater of the universe. And yet, Wolf 359 challenges this perspective. Its quiet existence redefines what it means to last, to persist, to survive. In a universe where giants live fast and burn out spectacularly, the red dwarfs, small, dim, and slow, write a narrative of extraordinary longevity. They do not seek attention. They do not blaze across the heavens to impress or dominate. Instead, they simply continue, steadily consuming their fuel methodically and efficiently, stretching their lives across not billions but trillions of years. Consider the scale. Our sun, a medium-sized star, will burn for about 10 billion years. Wolf 359, in contrast, has enough fuel to keep shining for up to 10 trillion years. That is not merely a long time. It is a time span so immense that entire galaxies will vanish. The cosmic tapestry we know will be unrecognizable, and black holes will reign in the cold, expanding void. The night sky, as we see it today, brimming with brilliant stars, will be ancient history, yet Wolf 359 will remain, a quiet ember resisting the encroaching dark. Its persistence is a cosmic patience beyond anything humanity has ever experienced. Even in the distant future, when the universe has cooled toward absolute zero, when star formation has ceased and galaxies have drifted apart into empty isolation, Wolf 359 will still emit light. Faint, unremarkable to casual observers, yet stubbornly persistent, it will stand as a solitary witness to a cosmos that has otherwise fallen silent. Imagine a theater after the final act. The crowd's gone, the lights dimmed, yet in the back row, one figure remains, watching, enduring, whispering through the ages. I am here and I remain. The secret of this longevity lies in the star's internal mechanics. Unlike our sun, which burns through its hydrogen in the core and leaves the rest untapped, red dwarfs like Wolf 359 are fully convective. Their interiors constantly stir, cycling hydrogen from the outer layers into the core, leaving no fuel unused. This meticulous, methodical process stretches their lifetimes across trillions of years. It's an elegant, minimalist design, a model of cosmic efficiency, a star that refuses to burn recklessly, that refuses to waste. Yet Wolf 359 is not entirely benign. Though its light is gentle, its proximity, just under 8 light-years away, means its gravitational influence is not negligible. Stars, after all, are not fixed in place. They orbit, they drift, they are nudged and jostled by invisible forces, by the gravity of unseen objects, by rare cosmic collisions. A rogue star can be a silent agent of chaos. Should Wolf 359 ever be displaced onto a path intersecting our solar system, the consequences would be dramatic. Its gravity could pull planets from their orbits, disturb the distant Oort cloud, and send comets hurtling toward the inner solar system. And all of this without ever needing to explode. Its danger is quiet, subtle, and indirect, but very real. The possibilities grow stranger still. Red dwarfs are faint, dim, almost invisible to the naked eye. If Wolf 359 were accompanied by a dark companion, a black hole or a brown dwarf, the pair could traverse the galaxy largely unnoticed until their effects became undeniable. The universe is full of surprises hidden in plain sight, and Wolf 359 may harbor secrets of its own, waiting to be revealed in a far future we cannot yet imagine. In this quiet, patient glow, there is a lesson for us. Human existence is fleeting, a momentary flicker compared to the slow, deliberate endurance of a red dwarf. Yet Wolf 359 is a reminder that longevity has its own power. Not all influence comes from brilliance or spectacle. Some of the greatest impact comes from simply persisting, from being there, quietly, against the odds, across epochs and eons that dwarf our comprehension. And perhaps one day, in a universe unimaginably far in the future, a civilization born from the remnants of galaxies long gone might look up to the faint red light of Wolf 359 and know. This light has endured, a remnant of a cosmos that once was a monument to patience, resilience, and quiet survival. It is a star that does not demand our attention, yet in the grand scheme of all existence, it may outlive almost everything else, whispering across the void that the simplest, slowest flames often burn the longest. Even in its ordinary, understated existence, Wolf 359 challenges our understanding of cosmic time. It invites us to reconsider what matters in the grand narrative of the universe. There is no spectacle, no final explosion, no fireworks. Instead, there is enduring presence, steadfast light, and the knowledge that sometimes survival is not about being the brightest or the loudest. It is about outlasting everything else, quietly, persistently, against the backdrop of a fading universe. This is Wolf 359, a tiny, unassuming red dwarf, quietly blazing for trillions of years, a cosmic survivor, a patient witness to the slow, inexorable unfolding of time. And in that quiet endurance lies a story more profound than any supernova, more humbling than any galactic collision, the story of persistence, patience, and the subtle power of simply being. But it gets worse. Red dwarfs are temperamental by nature, small, dim, and unpredictable. Their surfaces churn with violent magnetic energy, releasing sudden flares that can blast out radiation with almost no warning. Imagine a storm that doesn't just knock out your Wi-Fi, but obliterates an entire planet's atmosphere. That's the kind of tantrum a red dwarf can throw. And Wolf 359, though not the worst of its kind, still has its outbursts. Picture a solar flare so powerful it scorches every satellite orbiting a human colony, fries communication arrays, and silences power grids in seconds. Entire worlds plunged into radio silence. It's the cosmic equivalent of a reclusive neighbor suddenly storming out and flipping over the dinner table. But maybe, just maybe, the story of Wolf 359 isn't one of fear, but of dependence. Because when our own sun swells into a red giant billions of years from now, Earth will be nothing more than a cinder drifting through space. We'll need somewhere else to go, somewhere stable, long-lived, and dependable. Red dwarfs, for all their quirks, could be the best real estate in the cosmos. They burn slowly, living for trillions of years, far longer than stars like our sun. So even if Wolf 359 is a bit moody, it might still be a better landlord than a dying sun. The threat might actually be the invitation. So could Wolf 359 someday drift close enough to disturb our solar system? Could it fling comets toward Earth or tug our planet off its axis? Probably not. But the universe is an ancient and unruly place, about 13.8 billion years old. That's more than enough time for the improbable to become inevitable somewhere, somehow. Which means when it comes to this faint, unassuming star just 8 light years away, we'd be foolish not to pay attention. Because in the grand game of the cosmos, even the smallest players can upend everything. Wolf 359 isn't done telling its story, and neither are we. You know, for a star barely larger than Jupiter, it carries an air of mystery that's hard to ignore. It's like that quiet house at the end of the street, the one with no lights on, no noise, but a faint hum you can't explain. You tell yourself it's nothing, but you can't help wondering what's really happening inside. And that's where things get interesting. Could Wolf 359 be hiding something artificial? Imagine you're part of an alien civilization. You've survived the messy phase of history, wars, environmental collapse, arguments on galactic social media. Now you've mastered energy itself. What's your next move? You build, not a city, not a planet, but a structure around your star. This is where the concept of megastructures comes in. Not fantasy weapons or cartoonish sci-fi gimmicks, but genuine, mathematically possible feats of engineering. Structures like a Dyson sphere, or more accurately, a Dyson swarm. Countless solar collectors orbiting a star, gathering its energy like bees sipping nectar. Or maybe a Dyson bubble floating on light pressure itself. Or perhaps, if you prefer the poetic touch of fiction, a ring world. An enormous spinning ring encircling a star, its rotation creating gravity for the civilizations living along its inner surface. These aren't just dreams. They're serious proposals within theoretical astrophysics, humanity's best guesses at what advanced species might build when planets are no longer enough. And crucially, such civilizations wouldn't choose just any star for their project. They'd want one that's steady, slow-burning, and long-lived. In other words, a red dwarf. Now picture this. Somewhere in the galaxy, a civilization that thinks not in centuries but in millions of years seeks refuge. Their original sun has died, or perhaps it was never bright enough to sustain them. So they migrate to a red dwarf, because red dwarfs are cosmic survivors. They sip their hydrogen instead of guzzling it, and they can burn for trillions of years, longer than the universe has even existed so far. For beings who plan on cosmic timescales, red dwarfs are perfect. Dim, yes, but if you've built vast light harvesting mirrors or energy collectors, dimness isn't a drawback. In fact, it's an advantage. Less glare, fewer flares, easier thermal control, and the faint light makes it that much simpler to hide. A civilization could build quietly, shielded from detection. They could angle their collectors to reflect light back toward the star, camouflaging themselves in the glow. From Earth, we'd see only the faint shimmer of Wolf 359, unaware that entire worlds might be circling invisibly within its orbit. But what if they made a mistake? What if, for just a moment, the disguise slipped? We'd catch it as an infrared excess, a whisper of heat radiating into the darkness, a cosmic radiator glowing not in visible light but in wavelengths our telescopes can feel. Or maybe we'd notice irregular dimming patterns, unnatural shadows crossing the star's light. That's how the mystery of Tabby's star began, a flicker that sparked global speculation about alien technology. And even if the truth turned out to be dust, the question lingered, what if one of these flickers wasn't natural? What if we finally caught someone in the act of engineering a star? That would change everything. It would mean we're not just watching the cosmos, we're part of a much larger story, one that includes civilizations ranked by the Kardashev scale. Type 1, a species that harnesses the energy of its planet. Type 2, one that commands the power of its entire star. Type 3, masters of galaxies. A Dyson swarm would mark the jump from Type 1 to Type 2, a leap into cosmic adulthood. And if Wolf 359, sitting quietly only 8 light-years away, turned out to host something like that, then every map of the night sky would need rewriting. But here's the poetic part. Despite its proximity, Wolf 359 is so dim you'd never notice it with the naked eye. You have to seek it intentionally, to look deeper than the obvious. And maybe that's the lesson. The universe doesn't always hide its secrets in blazing supernovas or galaxies ablaze with light. Sometimes the real wonders are tucked away in the dark, quiet, steady, waiting to be found. Wolf 359 invites us to look closer, to question what we think we know, to wonder not only about what's shining, but what might be deliberately missing. Maybe there's no Dyson swarm. Maybe it's just a lonely star burning in silence. But asking the question, imagining the possibility, pulls us closer to understanding both the cosmos and ourselves. Because when we peer into the dark, searching for life, for meaning, for echoes of intelligence, we're really searching for our place in it all. And perhaps that's the point. Not to find proof of aliens orbiting Wolf 359, but to remind ourselves that we too are capable of curiosity, vast enough to fill the void. So the next time you step outside and stare into that endless black sky, remember, somewhere out there, a faint red glow burns steadily, patiently, waiting. 7.9 light-years away, our quiet neighbor, our mirror, our question mark among the stars. But let's pull the camera back even further. Way past the edge of our solar system, beyond the glittering constellations we can name, past the familiar stretch of stars that have guided humans for millennia, and into the uncharted vastness of interstellar space. Imagine for a moment, if humanity ever leaves Earth for good, where would we go? What kinds of stars would illuminate the paths of our interstellar journey? If your first thought immediately drifts to dazzling, powerful stars like Sirius or Rigel, then pause. Those celestial giants with their blinding brilliance are not our safest bet. Instead, some of the universe's humblest, dimmest stars, tiny red embers like Wolf 359, may hold the key to our cosmic future. So why aim for a diminutive red dwarf instead of a flamboyant blue giant? The answer begins with longevity. Red dwarfs are the slow-cooked meals of the cosmos. Their nuclear fires burn at a modest, steady pace, allowing them to outlive the majority of stars in the galaxy. Wolf 359, for example, is already over 1 billion years old and could persist for another 10 trillion years. 10 trillion. That's not just long-lived. It's practically eternal on a human timescale. For a species just beginning to venture beyond its home planet, stability and longevity are everything. We don't want to settle near a hotshot blue star destined to explode in a few million years. We need neighborhoods that endure, places where we can build, grow, and maybe even feel at home. Now imagine the scale of this vision. Generation ships, immense vessels carrying entire human communities, drifting silently through the dark expanse for centuries, perhaps even millennia. Their destinations aren't flashy stars hundreds of light years away, but the nearest red dwarfs within reach. And there's a good reason for this. Red dwarfs are the cosmic majority, making up roughly 3/4 of all stars in the Milky Way. They are not rare, exotic anomalies, but plentiful, reliable beacons scattered throughout the galaxy. These stars form an interstellar network, a chain of rest stops on a galactic highway, inviting patient explorers to travel from one safe harbor to the next. Our expansion might not resemble giant leaps across the void. Rather, it could be a steady, deliberate island hopping across red dwarfs, a methodical march of humanity through time and space. Despite their faintness in visible light, red dwarfs are far from energy poor. Their radiation, often concentrated in the infrared spectrum, offers a consistent, manageable source of energy, ideal for solar arrays or advanced power harvesting technologies. They are generally calm stars, past their volatile youth, providing stable environments for colonies. Planets orbiting these stars can be tightly bound, moving in days or weeks rather than years, resulting in short seasons or tidally locked worlds where one side basks in eternal daylight while the other remains in perpetual night. Strange and alien, yes, but potentially very livable with the right technology. Picture a generation ship arriving at Wolf 359 centuries from now. Passengers, most of whom have never seen Earth, and know it only through stories passed down for generations, peer from the observation deck at a modest red dot in the darkness. It is quiet, understated, yet steadfast. A new home. Massive solar sails unfurl to gather energy, drones scan for ice-covered moons, asteroid belts, or planets ripe for terraforming. Slowly, humans begin to build. Orbital habitats spinning in the void, self-sustaining ecosystems, hydroponic farms feeding entire communities. Wolf 359 evolves from a distant star in a catalog to a hub of human civilization, a seed from which future interstellar journeys will sprout. This slow, deliberate approach to colonization has captured the imagination of scientists and science fiction writers alike. Instead of a frenzied dash across the galaxy, humanity could advance methodically, star by star, red dwarf by red dwarf. Each system becomes a node, a foothold in space, and as colonies flourish, the knowledge gained there makes the next step easier. And with red dwarfs' extraordinary lifespans, each outpost has billions or even trillions of years to grow, evolve, and perhaps eventually forget the world from which it came. It's not flashy, it's not fast, but it is sustainable, intelligent, and entirely within the realm of possibility. Science is catching up to imagination. Researchers at SETI and other institutions have examined red dwarf systems not only for extraterrestrial life, but for human habitability. They study energy potential, stellar stability, radiation levels, and planetary environments. What they find is encouraging. If planets orbit within a habitable zone, close enough for warmth, distant enough to avoid scorching, they could sustain life, human or otherwise. Yes, challenges exist, from tidal locking to potential stellar flares and limited visible light, but none are insurmountable. Some red dwarf systems, including Wolf 359, are already under close observation as potential candidates for future exploration. With advancing technology, a rocky, warm, life-friendly planet might be detected sooner than we think, transforming speculation into actionable plans. Stars like Wolf 359 are far more than mere points on a chart or objects of curiosity. They are opportunities, gateways for humanity to build resilient, long-lasting civilizations. They redefine colonization as patient planting rather than conquest, emphasizing endurance over spectacle. Red dwarfs may not dazzle the eye or dominate the imagination, but they promise something far greater, a chance for humanity to extend its roots into the galaxy, slowly, deliberately, and with the promise of survival measured not in centuries, but in billions of years. Red dwarfs may not dazzle the night sky with the brilliance of stars like Betelgeuse, Orcus, or Vega. Their light subtle, often overlooked, yet they possess a remarkable kind of endurance, a quiet, persistent glow that can last for trillions of years. In the grand narrative of the galaxy, where stars flare brightly only to burn out quickly, these unassuming embers become the steady companions of time itself. For civilizations looking to anchor themselves among the stars, or for explorers charting the far reaches of the Milky Way, a red dwarf is the kind of celestial ally you hope to find: reliable, enduring, patient. And yet it begs the question, if red dwarfs are such cosmic idealists, could we be missing a hidden history? Could civilizations, ancient and forgotten by time, already have found a home among these stars? Perhaps somewhere in the dim glow of a red dwarf, life has taken root, evolved, and flourished while we have searched elsewhere, our instruments tuned to the wrong signatures. These stars, quiet and unassuming, may already harbor tales of existence we are only beginning to imagine. Take Wolf 359, for example. Small, faint, and distant, it doesn't compete with the luminaries of our sky, but it holds secrets written in the very elements that make up its being. To truly understand a star, one must look beyond its light, as seen by the naked eye, and into its chemistry, the molecular whispers that reveal its past, its potential, and even its character. A star is more than a point of light. It is a story in fusion, a chronicle of cosmic evolution. Imagine holding a prism up to the light of Wolf 359, letting its faint photons refract into a spectrum of colors, a rainbow of cosmic information. Each color, each line of light is a barcode, a signature left by the elements dancing within the star. Hydrogen pulses with a certain brilliance, helium hums slightly differently, and traces of heavier elements, calcium, iron, magnesium, sodium, leave subtle yet telling impressions. These are absorption lines, markers of the star's journey, akin to passport stamps tracing the star's origins and what it has carried through the galaxy. Wolf 359's composition is deceptively simple. Its primary ingredients are hydrogen and helium, the universe's foundational elements. Together, they make up over 99% of the star's material. Yet hidden among these elemental titans are faint traces of metals, astronomical metals, that is, elements heavier than helium. Unlike the iron or copper of Earth, these metals are the building blocks of planets and life itself. But compared to our sun, Wolf 359 is metal poor, possessing only modest amounts of these crucial components. Its low metallicity marks it as ancient, a relic of an earlier epoch when the galaxy's chemical pantry was still sparse. Stars, in a sense, are generational storytellers. The earliest stars, born shortly after the Big Bang, were almost pure hydrogen and helium, living brief, explosive lives. In their deaths, they forged the heavier elements: carbon, oxygen, iron, the essential materials of planets, atmospheres, and life itself. Subsequent generations inherited these cosmic legacies, gradually enriching the galaxy with the ingredients needed for complexity. Wolf 359, by contrast, emerged from an older, less enriched region of the Milky Way, carrying fewer of these heavy elements. Its chemical simplicity is like a sparsely furnished apartment, functional, capable of supporting life in the broadest sense, but lacking the abundance seen around younger stars. Yet even in its apparent austerity, Wolf 359 is far from unremarkable. Spectroscopy reveals whispers of ancient supernovae, the echoes of long-dead giants that once scattered metals across the galaxy. calcium, iron, magnesium, sodium, all present, subtle but telling. These trace metals indicate the star likely formed more than 7 billion years ago, older than our sun, a slow-burning sentinel from a bygone galactic era. Wolf 359 is, in essence, a living fossil, a miniature time capsule preserving the chemical conditions of the galaxy at a time when Earth did not yet exist. The implications for planetary systems are equally fascinating. Stars rich in metals are often surrounded by complex planetary architectures, worlds with iron cores, tectonic plates, and atmospheres capable of supporting life. Low metallicity stars, like Wolf 359, may struggle to form fully Earth-like planets. Yet even without the abundance of heavy elements, planets can and do form around red dwarfs. The sheer number of these stars, combined with their extraordinary lifespans, suggests that red dwarfs could host a significant fraction of all planets in the galaxy. They may not create Earth 2.0, but they could craft humble, resilient worlds, modest in scale, simple in design, yet remarkably enduring. Moreover, a star's chemistry is intertwined with the potential habitability of its planets. Red dwarfs are often prone to flares, intense bursts of radiation that can strip atmospheres and scorch surfaces. Wolf 359, however, is relatively calm, a slow-burning star whose infrequent flares and gentle energy output create a more stable environment. A planet situated in its habitable zone could enjoy geological and atmospheric stability over unimaginable spans of time, providing the conditions necessary for life to evolve, adapt, and thrive. And it all circles back to chemistry. The fusion of hydrogen into helium within Wolf 359 is more than a mere process of energy production. It is the heartbeat of the star, a perpetual engine shaping magnetic fields, driving stellar winds, and encoding the star's story in the spectrum of its light. Consider a thought experiment. A single teaspoon of material from Wolf 359's core. This plasma would be denser than any terrestrial metal, hotter than anything in our solar system, and yet fundamentally simple, elemental, and profoundly ancient. It would be a direct connection to the early universe, a tangible piece of cosmic history, and perhaps a hint at the future still to come. As the galaxy ages, the prominence of red dwarfs like Wolf 359 will only grow. In a future where stars like our sun have burned out and faded, these enduring embers will remain, softly glowing, stubbornly alive, the ultimate survivors of a once brilliant stellar population. To study Wolf 359 is not merely to understand one star, it is to glimpse the long-term trajectory of stellar evolution itself, to witness the quiet persistence that may define the universe billions of years hence. And so we arrive at the end of this cosmic journey, having traveled across light years and epochs, having traced the faint chemical fingerprints of an unassuming star, and having glimpsed the extraordinary endurance hidden within the ordinary. Wolf 359 may not light up our night sky with spectacle, but in its quiet persistence, it tells the story of the galaxy, the passage of time, and the enduring potential of stars to illuminate the future in ways we are only beginning to comprehend. From the outside, Wolf 359 appears almost laughably insignificant. To the unaided eye, it is nothing more than a faint, almost imperceptible smudge against the vast black canvas of space. You could spend a lifetime staring at the night sky and never notice it. And if you had stumbled upon its name today, it might have seemed like a footnote in a cosmic ledger. Yet, in a matter of moments, our perception of this unassuming red dwarf transforms. Suddenly, Wolf 359 is no longer a mere point of light. It becomes a quiet rebel, a celestial underdog, a star no larger than a giant planet and darker than the deepest shadows of a moonless night. And still, despite its diminutive size and modest brightness, its legacy stretches farther than that of many stars 1,000 times its magnitude. There is something almost lyrical about Wolf 359. It has spent eons in the shadows, unnoticed and uncelebrated, a cosmic wallflower existing without spectacle or fanfare. It never ignited myths, never dominated the tales of ancient skywatchers, never became the crown jewel of some dramatic constellation. For millennia, it was literally invisible to humans. And it wasn't until the 20th century, when telescopes and astronomical surveys grew powerful enough to pierce its quiet existence, that we became aware of it. Even then, it elicited little excitement. No headlines, no viral bursts of admiration. just a modest red dwarf quietly orbiting in a remote sector of the Milky Way. And yet in that very modesty lies its profound beauty. Wolf 359 teaches us that the universe does not always announce itself with thunderous spectacle. Sometimes the cosmos whispers. It offers its truths not to the distracted observer chasing brilliance and noise, but to those willing to notice the subtle, persistent, and enduring. In a galaxy of blazing supernovae and incandescent giants that burn with a fiery urgency and fade in dramatic explosions, Wolf 359 plays a different game. It is a marathoner, not a sprinter. It burns slowly, conserving its hydrogen, ensuring its survival for a timescale almost incomprehensible to human minds, trillions of years. Consider that for a moment. Our sun, halfway through its mere 10 billion year lifespan, pales in comparison. Wolf 359 has barely begun. Long after the sun has swelled into a red giant, consuming Mercury, Venus, and perhaps Earth itself, Wolf 3359 will still endure, quietly illuminating its corner of the galaxy. The endurance of this diminutive star carries a lesson for humanity. If we ever venture beyond our home planet in search of new worlds, we will not seek blazing suns like ours. They are too volatile, too short-lived. We will look instead for stars like Wolf 359, those that burn patiently and persistently, offering the stability necessary for life to thrive across unimaginable stretches of time. Its quiet persistence is an emblem of longevity, a reminder that survival and influence do not require flamboyance. Wolf 359 is also deeply relatable. We live in a world captivated by the immediate and the spectacular. We often overlook what lingers quietly in the background, assuming significance is synonymous with attention. But some of the most important truths are hidden in the subtle, the unobtrusive, the modest. For decades, this star went unnoticed, uncelebrated, deemed unworthy of our gaze. And yet, within that tiny dot of light, 7.9 light years from Earth, lies a narrative of endurance, resilience, and quiet power. Its story reminds us that not all influence demands applause, that true strength often manifests not in brilliance but in constancy, and that silence can conceal profundity. If Wolf 359 were at a social gathering, it would be the person leaning casually in a corner, quietly observing, sipping something unassuming, speaking little, yet possessing an understanding far beyond the chatter of the room. This is often how scientific discovery unfolds. Groundbreaking insights do not always emerge from obvious places or spectacular experiments. Sometimes they appear quietly from overlooked corners, from phenomena easily dismissed at first glance. In this sense, Wolf 359 mirrors our own lives. Small in scale, easily ignored, yet brimming with potential and enduring significance. Think about it. This seemingly insignificant star has survived billions of years and promises to persist for trillions more. Only recently have we begun to grasp even a fraction of its story and its importance. How many overlooked ideas, unnoticed individuals, or hidden wonders exist on our own planet, waiting for patient eyes to recognize them? Perhaps the ultimate lesson of Wolf 359 extends beyond astronomy. Perhaps it is a meditation on attention, awareness, and the humility required to see what is quietly enduring around us. Red dwarfs like Wolf 359 dominate the galaxy. They make up more than 70% of all stars, yet few can name even one. The universe in its overwhelming scale is largely composed of these quiet, long-lived stars, often missed because they do not scream for notice. In contemplating Wolf 359, we come to understand that the norm, not the exception, carries the seeds of longevity and stability. If extraterrestrial life exists elsewhere in the galaxy, there is a strong chance it revolves around a red dwarf, perhaps even one akin to Wolf 359. Humanity's gaze may have been misdirected all along, chasing the brilliant and spectacular, while overlooking the slow-burning foundations that quietly sustain the cosmos. Now, as you consider the tale of this humble red dwarf, think of the paradox it embodies: invisible yet indispensable, ordinary yet extraordinary, silent yet enduring. Wolf 359 did not seek fame, did not stage a cosmic drama, and yet, simply by existing and persevering, it leaves a mark on our understanding of the universe. It teaches us that the cosmos is not merely a theater of explosions and flares, but a patient, layered, and enduring entity. The next time the night sky stretches above you, resist the urge to seek the obvious, the belt of Orion, the shimmering dance of Venus. Instead, pause and consider what you cannot see, what lies just beyond your immediate perception. Wolf 359 is out there, steady, quiet, enduring, and it is far from alone. Countless tiny stars, overlooked moons, wandering planets, and silent celestial signals await those curious enough to ask, what else have we been missing? In their quiet persistence, they remind us that significance often whispers and that lasting impact rarely needs to shout.